of course, finally, Madam gave. I think let us take all those suggestions in a very positive spirit. Let us try to work even with more sincerity, with more dedication. Because as I said, rice is something without which food security, not only of this country, but probably global food security also cannot be imagined. Without rice, it is not going to be fulfilled. There are challenges in rice, and today, and then of course in subsequent days, we will be discussing in great detail of all of those. And let us try to develop a very sound action plan. And the recommendations of this conference should really help us in streamlining the research activities of not only NRI, but also IIRR. And Dr. Sundaram is here. And again, let me tell you, all the rice researchers, particularly these two institutes, NRI and IIRR, they must be working in very, very close coordination, very, very close coordination. So thank you very much once again. And today, we are really honored. Paramasaram, am I online? Whether Dr. Khush can hear me? Okay. Sir, am I audible?
Yes, I can hear.
Okay, sir. Thank you very much. Friends, it is indeed a great honor for me and for all of us to welcome Dr. Khush, who is not only a luminary, not only a great researcher, but probably mentor of almost every researcher working anywhere in this world. So, sir, thank you very much for kindly agreeing to our request and delivering this very important Dr. Khush. Those who are working in rice, they know the contributions of Dr. Khush. Even otherwise also you know it. But let me, particularly for our young scientists and students, let me introduce Dr. Khush, the great personality. Dr. Gurdev Singh Khush was born in Roorkee, Punjab on August 22nd, 1935. If you miss the year, I repeat 1935. And received his BSc Agriculture degree in 1955 from Government Agricultural College, now Punjab Agriculture University, Ludhiana, and PhD in 1960 from University of California, Davis. After serving as an assistant geneticist at University of California, Davis, for 7 years, he joined International Rice Research Institute, Los Banos, Philippines in 1967 as a plant breeder. Then he became head of plant breeding department in 1972, became principal plant breeder and head division of plant breeding genetics and biochemistry in 1986. He superannuated from IRI in 2002, wherein he served for 35 long years. Professor Khush joined the University of California, Davis again as an adjunct professor in plant sciences department. Friends, some few years back, I was attending an international conference on rice, and there one renowned rice scientist summarized the contribution of Dr. Khush like this. He said, if you are standing any rice field anywhere in the world, you can be sure that that particular variety has directly or indirectly has got something to do with Dr. Khush's contribution. And this is the contribution. Dr. Khush is recipient of many, many prestigious awards. I shall not read all, but just few. Padma Shri in 2000 from, of course, President of India. Borlaug Award 1977. World Food Prize in 1996. Japan Prize in 1987. Rank Prize in 1998. Wolf Prize in Agriculture, 2000 DSc degrees from 10 universities, including Cambridge University and Ohio State University. He was elected fellows of almost all the national academies of the world and certainly of our country. His research achievements I simply summarized, so I shall not repeat all those. Presently, Dr. Khuz works as adjunct professor in UC Davis, California, and he is very actively involved in Gurdev Singh Khuz Foundation for Advancement of Agricultural Sciences, which was established in 2010 with the generous donation of $7,000, which is approximately 3.5 crores by Dr. G.S. Khuz, which provides financial support to promote education, research, and training in agriculture. He continues to being a mentor, lecturer, and of course, to consult various programs nationally as well as internationally. So with these few words, sir, once again, I welcome you. And it is indeed a great honor for all of us, particularly those who are working in the field of rice science and also others who are directly or indirectly associated with agriculture. Thank you very much, sir, for kindly agreeing to our request. And now I request you to kindly deliver the talk. Over to Dr. Khuz, please. Thank you.
Thank you very much, Mr. Director. It's very kind of you to give such a generous introduction. I was really delighted when I received the invitation from Pawan Agarwal, and I was very, very excited that I will have the opportunity to interact with the rice research workers of our country. I have very fond memories of visiting in RRI. Of course, at that time it was called Central Rice Research Institute, and I visited many times. My first visit was in 1968. Perhaps some of you, some of the participants may not have been born at that time. But I have a tremendous respect for the rice research workers of our country, for their contributions. And of course, the contributions are very well known. Because of their efforts, India has become the world's largest rice exporter. I understand that India exported 20 million tons of rice, and this contributed to world food security because there is a shortage of food grains. So India exports rice and wheat for meeting the food needs of many countries which need the help. So with those few words, let me start the presentation. Could I please screen share myself? So let's look at the first slide. Okay, sorry for the confusion a little bit. So you can see that the rice production in India has increased more than 4 times since 1960. The total rice production at that time was 34 million tons. Now we have 120 million tons. That's really a tremendous achievement. And this is the tribute to the Indian rice scientists, the former and the present. And this is a very, very admirable contributions. So what is in spite of this tremendous achievement, there are still food security problems. So there are 200 million Indians who are food insecure due to lack of purchasing power. Although we have abundant food, which we are exporting, but then this is a dilemma where we have 200 million Indians who are food insecure. This is because of lack of purchasing power. As the purchasing power increases, this problem will not exist. And 40% of the children below 5 years of age are malnourished and stunted. This is a very serious problem. And then, of course, there's a widespread malnutrition. So what are the problems facing the Indian agriculture? We have to, so that we can address those problems in the future. So one is crop varieties have low yields and poor nutrition. You can see that the rice yield average is little less than 4 tons, whereas China and Japan, they have over 6 tons. So as compared to them, our rice yields are still somewhat lower, and they have poor nutrition, meaning they lack some of the micronutrients. Then we have degraded soils, which is the main reason we cannot get those very high yields. And we have, of course, stressed water resources and poor crop diversity. So what are the research approaches? Of course, we have to develop the resilient crop varieties using breakthroughs in genetics and molecular biology. That should be a very big focus. Then, of course, to eliminate malnutrition, we need to develop biofortified crop varieties. Then improve soil health, improve water management, and improve the crop diversity. These are some of the research approaches. And I will spend major part of time on the genetic improvement, then of course little bit on the management side. So there are a lot of opportunities now use the various breakthroughs in molecular biology, genetics and molecular biology. And one, of course, is the identify the useful genes for rice improvement. Here are some of the new genes which have been identified recently in different crops, like KRN2, which increases the number of grains in maize. OSTRR increases the number of grains in rice. Then there are Highlander gene in Arabidopsis, which can produce sterile progenies, which can be used for hybrid production. And there is a gene in wheat for inhibiting biological nitrification. These are some of the recently identified genes for crop improvement. Application of gene editing for crop improvement. This is one of the very important recent breakthroughs where we can use the gene editing for different mutations or improve the existing problems which may be in the crop varieties. And it's very admirable that the central government has passed an order on March 28 that SDN1 and SDN2 types of gene editing will not require the regulatory processes which are stipulated for the GM crops. So I am sure many of our rice scientists must be working using this gene editing technique for improving the rice. So there are several examples of gene-edited crops which have already been released, which are being grown. Powdery mildew-resistant wheat is one example. Gene-edited barley is another example. Gene-edited potato is the other example. These are some of the recent developments, the varieties which have been developed through gene editing technique. See here, this is the powdery mildew resistant wheat, which is now being introduced for the on-farm production. Very important resistance to very important disease. Then there is this problem with barley. There are many barley varieties which are viviparous, or the grains start germinating in the panicle before harvesting. So this has been improved through gene editing technique. So the same variety is now does not have that problem. Very good examples of gene editing. Then, of course, we have genetic engineering, which unfortunately our country has not derived the benefits from the use of GM technology due to the moratorium on GM crops. Hopefully, this will become easier to introduce the genetically engineered or GM crops. And I understand there is a good news about the possibility of releasing GM mustard, or which will be very important for our country. And there are some examples of the genetically applied technique which have been very, very useful in many countries. And we had a first example, of course, the GM cotton. You can see the control. There is a lot of damage by this bollworm, pink bollworm, which really devastates the crop. And this is the BT cotton, which was the first GM crop introduced in our country. And it has benefited the farmers, it has benefited the country. We got doubled the production of cotton because of use of this technology. This is an excellent example of GM genetic engineering technique. You can see this is the BT corn, where BT gene has been introduced from Bacillus thuringiensis into corn. These are the BT varieties, and these are some of the damages shown by this European corn borer, which damages these crops, and these are resistant to the European corn borer. So this BT corn is grown now almost to 90% of the area in the United States, Canada, Brazil, Argentina, and this has contributed to food security. And although this BT corn, which is widely used, widely grown, and many of the products are using this BT corn in several products, like you take the case of chocolate. It's BT corn is present in most of the various products, but chocolate is just one example. Then we have BT brinjal. There was a lot of controversy a few years ago, but it has been released in Bangladesh. You can see this is the control, this is the BT brinjal. There's no damage. Here you have to use large number of pesticides. So this is a very good use of this technology. And there are varieties of different kinds. This is control. So sorry. Excuse me for 1 minute, please. Okay, this is another example of GM technology. GM wheat has been produced, which has a high level of drought tolerance. And these so-called H4 wheats have been now are being grown in more than 10 countries. So this drought-tolerant wheat is really contributing to the increase in the wheat production in several countries. So I want to discuss three very important projects which are, we call them man on the moon projects. These three projects actually started in 1990s at IRI, and there was a lot of interest because these are really high profile crops, high profile projects. So what is one is to improve the efficiency of photosynthesis. And the second is nitrogen fixing cereals. These we would not have any life on the planet if we did not have photosynthesis. Because without photosynthesis, we will not have any food. Similarly, nitrogen fixation is as important, because without nitrogen fixation, which is carried out by microbes, there will be no nitrogen, there will be no crop production. So those two very, very important very important natural processes are for this, which have led to the continue or the start of the civilization. Because without these two, without photosynthesis, without nitrogen fixing cereals, there will be no life on the planet. And third project is the apomactic rice, because that can help us in introducing the hybrids, which will need the seeds. Hybrid seeds will need very small or almost no extra cost. So they should be sold as regularly as non-hybrid varieties. So at IRI, this project was started to change the photosynthesis, because there are two types of crops, C3 and C4. C4 crops are almost 30% more efficient as compared to the C3 crops. You take the case of rice and wheat, they are C3, but maize is C4. That's why the yield of maize is much higher as compared to rice and wheat. So there was this project, one of those man on the moon projects, to explore if rice or wheat could be changed to C4. And first step was to see if, because there are changes in the anatomy of C3 and C4 plants, and a lot of germplasm was screened to see if any rice variety could be available which may have the anatomy of C4. But none of those varieties could be identified which have the anatomy of C4. So this project really could not move any further. But now there is a very strong interest in the United States to use a different approach. For example, the main enzyme in the photosynthesis is rubisco. And rubisco is used for converting the carbon dioxide and water into the carbohydrates through the use of this enzyme. Now, there are different types of rubiscos, because by screening the large amount of species, it has been found that there is a variation, quite a variation in the gene sequence of different rubisco from different crops, particularly the earlier ones, the ancient rubisco is quite different. So once you can identify the different sequences, you can select the ones which have more efficiency. So there's a lot of interest in this project and a lot of investment is going into it. Then there was a lot of interest at Erie to see if the rice could be converted into nitrogen fixation. And as you know, most of the nitrogen which is fixed by the cereals is through the microbes in the soil. But then there are the symbiotic type of nitrogen fixation, which is fixed by the microbes in the nodules of those crops. So effort was made to produce rice which had which had those which had the nodules. It was possible to produce the nodules, but the microbes did not start fixing any nitrogen, or microbes did not really function in these nodules. So there is a new project. It's a huge project, and I will come a little later. So apomictic rice is, as I mentioned, was one of the third Man on the Moon projects. And this project actually was started at Erie when I came here to to UC Davis, I talked with one of the scientists here, Dr. Sundaresan, and I talked with him if he could start using the molecular biology to fix the, to make the rice as, or introduce the apomictic situation in rice. And he worked for almost 20 years, and he has been very successful in having apomictic rice. And so he worked with the colleagues in France, and this collaborative project between UC Davis and France has resulted in the establishment of apomictic rice. You see, this is the F2 progeny. You can see the variation. And when you grow this F1, then it continues to breed through. So these are the apomictic hybrids, which you can just produce, start producing the seed like ordinary variety, and it will help to popularize this hybrid rice on a much larger scale, because the cost of the seeds will be just like the ordinary rice. So this has been one of the major breakthroughs, and the paper was published in Nature about 4 or 5 months ago. So hope you can look at it and start using this technique for producing the apomictic hybrids. Then, of course, I mentioned the malnutrition due to micronutrient deficiencies. And these deficiencies are iron, zinc, and vitamin A. Most of the cereals have only low amount of iron and low amount of zinc, and some of them have no vitamin A. So this is a project which has also received a lot of attention. There's a project called, sorry, before I go there, I just want to show you what are the consequences of this micronutrient malnutrition. So this micronutrient malnutrition is because of, it causes higher mortality, lower cognitive ability, lower work productivity, stunted growth of the children. These are some of the implications of malnutrition. So improving the nutritional status of children and the adults is a highly effective way to increase economic productivity in agriculture and other sectors. Because if people are healthy, they will be more productive and contribute more to the national productivity. So there was a international project called Harvest Plus. It was a CGIAR project. The focus of this project is to elevate the level of these micronutrients in different crops. So a lot of progress have been made. Almost 393 biofortified varieties have been released in 12 countries, in 12 crops in 49 countries. So you can see in these crops, beans, cowpea, lentil, and these are pearl millet. These have high elevated iron content. Rather than very low, it is adequate. Then, of course, we have zinc situation, which has been improved in maize, rice, sorghum, and wheat. So this high zinc rice has been distributed, released in several countries, and I understand almost 13 different biofortified varieties of different crops have been released in India. This project has been really very productive in producing these biofortified varieties. This is another good example of introducing the varieties with high vitamin A content. This is sweet potato, white sweet potato. It has no vitamin A, but this purple sweet potato has a very good amount of vitamin A. So this has been, these type of sweet potato varieties have been released in many African countries on a large scale through this Harvest Plus program. And this has been one of the achievements for improving the vitamin A content. Golden rice, I'm sure you have heard about this project. It was a really very long project. I think the work went on for 25 to 30 years. It took, finally, it was possible to produce this golden rice, which is golden color is because of the beta carotene. Beta carotene is converted into vitamin A in the human digestive system. So vitamin A deficiency is very prevalent in the rice-consuming populations, particularly poor people who derive most of their vitamin A from rice, which does not have any beta carotene. So this, as I mentioned, was a long duration project because it took quite a bit of time to go through the regulatory process. It has been finally released in the Philippines. It was released early last year. So seed multiplication has been going on, and the government produced more than 90 tons of golden rice, and they have distributed all over the country. So this is the first country where golden rice has been approved. I understand Bangladesh is in the process of going through the regulatory process, and it will be tested and evaluated in many other countries like Indonesia, Cambodia, and I hope it can also be evaluated in our country so that we can take the benefit of this breakthrough. Now I switch to the management aspects, and so the status of organic matter content in the soils of India is not adequate. So normally in this organic matter content, the surface of 20 centimeter of soils is less than 0.5% in most of the Indian soils. But for the optimum level, if it can be in the root zone from 2 to 2.5%, those soils will be much more productive as compared to the ones which have only 0.5%. So that should be the effort to increase the vitamin, to increase the organic matter content in our soils. So the crop soils of India should be ameliorated by improving the organic matter content. Recarbonization of soils is a long-term strategy, and restorative agriculture is the best solution. So this is where most of the nitrogen is fixed by the microbes in the root zone, and the amount of nitrogen fixed by the microbes is not the adequate level because of the low organic content of our soils. So what the effort should be to increase the organic matter in the soils so that more nitrogen can be fixed, because there are various kinds of microbes like bacteria, fungi, and nematodes. And if you take 1 spoon of soil, it may have 1 billion different microbes. So microbes are our saviors, and they feed us. They feed us because they produce the nitrogen on which the crops grow, produce the grains. So it should be, we should try to increase the organic matter. And this is one of the unfortunate situations where instead of putting the straw back into the soil, we are burning it. This is a very unfortunate situation. So the restorative agriculture should return maximum amount of biomass to the soil. It should use the minimum tillage so that the microbes can proliferate in the soil, spray microbial spray called Pusa decomposer on biomass so that it can expedite the decomposition and practice good crop rotations. Those are some of the approaches for increasing the organic matter in the soils. Of course, this is the so-called restorative agriculture, where the wheat is implanted in rice straw. And this is the best way to feed the microbes. Microbes are feeding us. We should feed the microbes by providing them more organic matter, like in this restorative agriculture. The next item is stressed water resources and impact on food security. This is a major problem in our country, where we are depleting the aquifers. In Punjab, for example, the water tables have gone down by 10 meters since 1973. At present, water tables are going down at the rate of 0.2 to 0.5 meters per year. And this is extreme example in Punjab, but this is similar situation is happening in many other states, because we are really depleting the water aquifers, and this is one of the major challenges, how to improve the situation. And the reason for this depletion of aquifers, this mismanagement of water resources. For example, this is the tubal irrigation, which is very wasteful, because a lot of water is wasted, and the reason is the free electricity, and farmers can switch the button for running these tube wells, and then of course sometimes they just go away, even sleep, and let the water run. This is very, very wasteful. So what are some of the policy interventions for improving the water management? So first is, of course, withdraw the subsidy for tubal irrigation. This is has done already a lot of harm, and it should be stopped. then start a direct sowing of rice instead of transplanting, thus saving 30% of the water, because a lot of water is needed for growing nursery, for making the puddling, and that takes almost 30% of the water in rice production. Policy intervention by paying farmers rupees 1,500 per acre if they direct sow rice. This is the policy intervention which has been introduced in Punjab to encourage the farmers to store rice, to sow rice rather than sow rice under dry condition rather than transplanting. Introduce drip irrigation, which uses 30% less water as compared to flood irrigation. It may not be possible in all crops, but at least we should try some of the crops where the drip irrigation is feasible and it takes 70% less water. Then use of short duration varieties is one of the interventions. Then reduce the area under rice in North India, definitely in Punjab, Haryana, Western UP, because that's where the major water problems are coming up. You see, this is so much water is needed for growing nurseries, then puddling, and that reduces uses much more water. And this direct sowing, as I mentioned, saves 30% water. Introduce crop diversity. This is becoming a very big issue so that we can reduce the monoculture of cereals and promote the cultivation of oil seed crops and pulses, because we spent almost $2 billion to import pulses and $2.2 billion for importing the oil crops or oil seed, edible oils. And you can see those are the very important issues which can be addressed by reducing the monoculture of cereals. And this is one good example where some of the wheat area should be taken out, plant to mustard, which is a good oil seed crop, and by growing diverting some of the area from wheat to mustard, we will reduce the importation of oils. For the rice, if some of the rice area can be converted to pulses, that's one of the good approaches, because rice is very productive and most of the pulses do not give the same kind of return. But there is one crop which is very appropriate for reducing the area under rice, and this is the soybean. Soybean is very productive, and we need also the oil from soybeans and also the protein. But the productivity of soybean in our country is not very high. Average yield of soybean in India is 1.1 ton. Brazil has 3.5, USA 3.75 tons per hectare. But most of the soybean in our country is grown under rain-fed conditions. But if you grow this with irrigation and with proper management, we can increase the productivity of soybean and produce more oil. So these are the pulses which can be used to replace some of the area under rice. Mung bean is one. Then there are several other pulse crops which are very suitable, because we need the pulses in our country and reduce the importation of pulses and convert some of the rice area to the pulses. Thank you very much. That's my presentation. And so I will stop sharing these slides, and I will be very happy to respond to any questions or comments.
Thank you, Professor, for your excellent and also comprehensive presentation. Now I would request Secretary Dar and DG ICAR, sir, for your remarks.
Thank you. Thank you. Thank you very much, sir, for a very enlightening lecture and highlighting some of the very serious issues of rice for India, and also providing some very useful suggestions. Of course, this man on the moon projects, NRRI, IIRR, I think many other institutes in ICAR also started working, and we are still working, and I'm sure with your guidance and collaboration with several other international organizations, there will be some success. Of course, there is some success in all these 3 projects which you kindly mentioned, including C3, C4, including apomictic hybrids, and of course, golden rice probably is going to be a reality. And you very rightly mentioned the government of India has already given permission for SDN1 and SDN2, and several projects for gene editing is going on within ICAR. And our scientists are also getting very closely associated. Again, your suggestion for soil recarbonization, water use efficiency enhancement, diversification. And not only from ICAR, but several state governments are also working. And probably you'll be happy to know that Punjab government is already working on which we call MMM. That is maize, moong, and mustard, so that some of the rice wheat areas can be diversified into these crops. So this MMM, cereal, pulses, and oilseeds, so this will also help us reducing our import of both the commodities, pulses as well as oilseeds. So, sir, thank you very much. Quickly, if any one of you have got any comment, of course, yes. Can you give a microphone, please?
Hello.
Thank you, Professor Khos, for an excellent presentation. In your first or second slides, you have mentioned about we are worried for that 200 million people are not getting food due to purchase power and other things. So I'll just add that throughout your lecture, we are expecting that due to climate change, there's a production and productivity of rice is reduced. So particularly in Odisha, we are worried for that. In every year or alternate years, we faced cyclone, drought, or flood. And most worrying is that suppose at the harvest stage, there is a cyclone or flood or some other natural calamities, how to face that? That is my worry from the Indian Climate Congress. I am the president of Indian Climate Congress and former Dean, OUT Bhuvan sir, Professor Samanta.
Thank you. Thank you very much, Dr. Samanta. Of course, Dr. Khos, I think you would like to give your response, because this is not only a problem of Odisha, this is a global problem. So probably very quickly, if you can give your kind response to this one, this will be benefiting all of us.
I think that's a very, very valid concern, because climate change is the major culprit, which is leading to this diversifying the rainfall, as well as various other problems like reducing the crop yields because of high temperature, and the variations we see in rainfall and drought and floods. That's really the serious concern all over the world. Here in California this year, we had a continuous rainfall, and year before there was a lot of drought. So this is contributing to the food security, and I am sure Odisha is not any different than many other areas. I think you have the problem of drought and floods, and which is unfortunate. So that's why there is so much emphasis on working on the climate change. So there's a worldwide effort to reduce the warming of the earth, and our country is participating in those international efforts.
Thank you. Thank you very much. Any other quick? Yes, sir.
Sir, thanks a lot. I'm very much delighted to hear your lecture. I had seen Dr. Kush only in the books when I read that books written on the area only. The important point is, in Philippines, yellow rice has been released. Now this yellow rice, can we go for parboiling, or can we make some products from the yellow rice? If you make yellow rice, any products or parboiling, how far it is successful technology-wise?
Thank you. Thank you very much.
Yes.
Sir.
I think excuse me. There has been experiments to see if you parboil the yellow rice or golden rice, what will be the situation, whether it will improve the availability of the vitamins, or will it deteriorate or reduce the vitamin A by parboiling. So this, I think there is a lot of experiments going on. This is a very good question, and we should know in 1 or 2 years.
Okay, thank you. Thank you very much. Okay, friends, I think every good thing comes to an end also. So we have to close or conclude this particular session. So, sir, thank you very much. मुझे तो यही लग रहा है कि इंडियन राइस कांग्रेस का सेशन हो और डॉक्टर गुरदीप सिंह का भाषण ना हो तो फिर राइस कांग्रेस असंपूर्ण अधूरा रह जाता है. सर, आपने वो कमी आज पूरा कर दिया, तो बहुत बहुत धन्यवाद आपको. From all of our on behalf of each and everyone who are present in this hall and those who have joined online, I thank you very much profusely, and may I request all of you to please give a standing ovation to Dr. G.S. Khuz for his lecture today, and of course for his enormous contribution for rice science of the world. Thank you. Thank you very much, sir. Thank you.
Thank you. It's my great pleasure. Thank you. And I was so delighted to participate in the second Rice Congress. Particularly, I am delighted that there are so many rice scientists working in our country. And of course, some of them were born after I joined Central Rice Research Institute in 1968. I visited first time, and I think many of the rice scientists we have are probably not even born at that time. So I have been fortunate to have spent my entire career working on this very important food crop, which feeds half of the world. The rice is staple crop of 50% of the world. 50% of the rice consumer depend on rice. So thank you for working on rice, for improving it, and thank you for organizing this conference. It has been my pleasure to join you during this second rice conference. Thank you.
Thank you, Professor. So now we would like to felicitate our Director General ICAR and Secretary for being the patron of the second Indian Rice Congress. I request Dr. Director Ekinaik sir to felicitate our DG sir. Thank you, sir. I request our director, Dr. A.K. Naik, sir, for official vote of thanks.
So I am having proud privilege to express my thanks to head of NARS family, Dr. Himanshu Pathak, for nicely conducting this session. And in fact, he was guiding for conducting this second Rice Congress. It is his brainchild. And we are conducting the second Rice Congress. The first Rice Congress was his brainchild. Now, because of the presence of our Honorable President, now it has got some legal status, and it will continue in future, sir, under your guidance. We will continue this, and the Rice Science will assemble, and we will continue to serve for the cause for which the Rice Science are espousing. Thank you very much, sir.
Thank you. Thank you very much.
Thank you. Thank you, sir. We come to conclusion of this plenary talk session. I gratefully thank all the participants, delegates, students, friends, especially Professor Kush for giving this excellent plenary talk. Professor, thank you. We would like to conclude the sessions. Please assemble by 2:15 for panel discussion. Thank you. It's 2:40.
So I would request you to be online again at 2:40 for panel discussion. Thank you. into the main program because DG is arriving, who is the chair of this panel discussion. Now, I would request, in order to save the time, to request the panelists to kindly be on the stage. I would be Dr. R.C. Agarwal, DDG Education ICAR, who is the co-chair of this session. Sir, please take your seat. And then Dr. S.K. Pradhan, ADG FFC ICAR. Dr. P.K. Agarwal, ADG TC ICAR. Sir, could you please come on the dais? And the panelist, Dr. R.M. Sundaram, Director IIRR. And we got also Dr. Jahor Ali from ED Philippines. He is joining online. And Dr. S. Mohanty from Asia Regional Director, International Potato Center. He is also online. And I would also request Dr. Birender Kumar from ED Philippines, who is here. Dr. A.K. Nayak, Director ICR NRRI. So, yeah, I learned that Dr. A.K. Nayak has gone to receive DG. He is accompanying him. So, just for your information, sir, there is one cordless mic in your table and also in this table. So you have to kindly hand over to the next panelist. Okay, thank you. Sir has arrived. Okay. Respected Dr. Himanshu Pathak, Secretary DR and DG ICAR, Dr. R.C. Agarwal, DDG Education ICAR, Dr. S.K. Pradhan, ADG FFC ICAR, Dr. P.K. Agarwal, ADG TC ICAR, all distinguished panelists, ladies and gentlemen. It could not have been better. The inauguration of the Second Indian Rice Congress by Honorable President of India and a plenary lecture by a World Food Prize laureate, Dr. G.S. Khose. I believe all of you are still overwhelmed by the morning session. Now we are to begin yet another exciting and thought-provoking session. The organizers have gathered a great panel of experts to discuss on the theme, Transforming Rice Research for Ensuring Food Security. This panel will argue on some pressing issues of Indian rice science, cultivation, policies, and farmers. We are really lucky to have Dr. Himanshu Pathak, Secretary DR and DG ICAR, as the chairman of this panel discussion, who has been the key in conceptualizing the first Indian Rice Congress while he was the president of ARRW. And we also lucky to get, as a co-chair of this session, Dr. R.C. Agarwal, DDG Agriculture Education. Thank you, sir. And all distinguished panelists, I'm just again naming them for the audience, Dr. S.K. Pradhan, Dr. P.K. Agarwal, Dr. R.M. Sundaram, Dr. Jahor Ali, he is joining online, Dr. A.K. Nayak, Director NRRI, Dr. Birender Kumar from ED Philippines, Dr. S. Mohanty from International Potato Center is also joining online. And this session would be convened by Dr. S. Shaha from ICR NRRI, who is also the organizing secretary of the Second Indian Rice Congress. And rapporteurs would be Dr. S. Samantaroy, who is the head of one of the division of ICR NRRI, and also Dr. G.A.K. Kumar, Principal Scientist, ICR NRRI. Without any further delay, I would like to request the convener, Dr. Sanjay Shaha, to introduce our chair and co-chair and panelists briefly to the audience. Thank you, sir.
Thank you, Kutub. Respected Dr. Himanshu Pathak, sir, our Honorable Secretary DR and DG ICAR, Dr. R.C. Agarwal, sir, DDG Education, all the distinguished panelists, ladies and gentlemen, thank you for all being here. It is my duty to briefly introduce our chair and co-chairs, as well as panelists present in the panel discussions will be chaired by none other than our DG sir, Dr. Himanshu Pathak sir. Actually, he needs no introduction to this audience. Everybody knows him. And sir, as you know, during plenary lecture, the concept of Indian Rice Congress developed by sir only. And sir, we are following your footstep only, sir. This Indian Rice Congress. Sir, as for youngsters, sir was director of National Rice Institute, Cuttack earlier. Then again, he was director of National Institute for Abiotic Stress Management, Baramati. He is one of the most important and renowned climate scientists in the world. And presently also, sir is heading our NAS faculty. Then our co-chair, Dr. Rakesh Chandra Agarwal, sir. He is currently serving as Deputy Director General, Agriculture Education, and also National Director for Government of India World Bank Project, National Agriculture Higher Education Project. Coming to the panelists, we are having today 5, 6, 7 panelists. First, Dr. SK Pradhan. He is aiding as ADG FFC at the headquarters. He is a famous rice breeder and developed more than 50 outstanding rice varieties and renowned rice breeder in the country. All these rice ecologies are across the ecologies, which in turn improve the farmer's livelihood and income. Dr. P.K. Agarwal, he is currently serving as ADG Coordination Headquarters. He also served the council and nation with many responsible positions. Earlier, he was former Vice Chancellor of Odisha University of Agriculture and Technology, Bhubaneswar, and also Assistant Director General, National Agricultural Science Fund at headquarters. And presently, Dr. Agarwal is President of Association of Rice Research Workers. Dr. R.M. Sundaram, he is heading the Indian Institute of Rice Research, Hyderabad, as Director. He is a well-known scientist of global repute, working in the area of biotechnology, molecular breeding, genomics, and developed one of the first biotechnology products in rice, that is improved Samba Masuri, with pyramided bacterial variation genes. Then Dr. Johar Ali, he is presently online. He is working as Research Unit Leader, Hybrid Rice at ED Philippines. He has revitalized the Hybrid Rice Development Consortium to meet the members and bring in value. Dr. Ali successfully released more than 60 multi-stress tolerant green super rice varieties through the collaborative efforts of colleagues from ED, CAS, and NARS. Then Dr. A.K. Nayak, he is leading our institute, the host institute, Dr. National Rice Institute, Cuttack. He has vast experience working on problem soil management, water quality mapping, modeling, management of poor quality irrigation water, the nutrient management in rice-based production system, and the budgeting of greenhouse gas emission in lowland rice ecology. Then Dr. Brinda Kumar leading the adaptive agronomy and pest ecology cluster of the Sustainable Impact Platform, ED Philippines. He also coordinates our direct seeded rice consortium for South Asia. His research for development program is focused mainly on sustainable and profitable integrated weed management for rice-based system. Then Dr. Samanindu Mahanti, he is leading Asia Regional for International Potato Center as director. He is also in online. He provides programmatic oversight for research and development portfolio. He provides leadership in the regional operation system and plays a representational role for CIP in the region with a focus on India and other South Asian countries. So with taking much time, now I request Dr. Himanshu Pathak sir to chair the session. And the dais is yours, sir. Thank you, sir.
Thank you very much, colleagues. Let us make it this session at least enjoyable, interactive. So there is no PowerPoint presentation. And all the panelists, you know very well the questions have been given and you have to answer that question. No formalities, no honorable in the beginning and no thank you at the end. Okay. So the process is each panelist has already been given 2 questions and they have to respond to these 2 questions in 2 rounds. So first question, first round, second question, second round. So easy. So try to be very, very specific. And let me tell you, my expectation is when this is over, we will be really, really learned by at least very latest things on the question which has been asked to you. First round, 5 minutes, no interruption. Only my clock will run and nobody will be asking any question. Second round, of course, again 5 minutes, but then there could be 1 or 2 things. And then at the end, we'll be taking questions from the floor to any one of you. Okay. So friends, let us have this very interesting and enjoyable round. Our first panelist is Dr. S.K. Pradhan, who is not known to CRI, I think. Oh, he's known there. Okay. And the question given to Dr. Pradhan is grain yield in rice already reached a plateau in India, at least in certain production systems or region? Dr. Pradhan, your time starts now.
Thank you, sir. Good afternoon, everybody. This is a good question. Is grain yield in rice is already reached? Is grain yield in rice already reached a plateau in India, at least in certain production region system? So, sir, this is, rice, it has different ecosystems, ecology. So in particularly harsh ecology, there is no question of this yield plateauing, yield ceiling. But in case of irrigated rice, probably we are reaching towards that. But recent research results show that in case of irrigated rice also, we have research results indicated that there is a break in yield ceiling. So in case of genome edited line, latest result shows that about 50% yield of that line is more in the edited line compared to the wild type one. So that is with respect to a single gene, that is GN1A. So if one gene is giving more than 50% of yield in case of irrigated rice, any ecology, so we cannot say that we have reached a plateau. But certainly for average productivity, average production in certain ecology like northeastern India, Punjab, Haryana, the irrigated rice ecology seems to be like a plateauing trend. If we expect about 8 ton, they have almost reached to 6 average yield of 6 ton paddy at least. So, but in case of rain-fed rice, particularly lowland and upland and other ecology, harsh ecology, we are not at all reaching to a plateau. It will take at least 1 or 2 decades to reach the plateauing. So there is a vast scope in case of lowland rice, where the production constraints are many. So those are to be taken care or addressed, then only there will be a reaching to a plateau point. So in my opinion, rain-fed rice, we have not reached, but in case of irrigated rice, we are reaching, but certainly the yield potential will be further enhanced. There will be another jump like the train we are getting. There will be again a quantum jump we may achieve. This is my feeling, but currently it seems to be like a plateauing of yield for irrigated rice. Thank you.
Thank you, Dr. Pradhan, for very specifically responding to this particular question. Friend, I think 4 or 5 years back, in one presentation, Dr. Pradhan gave me a concept of what is called as Kalpadhan. Kalpadhan means dhan of your imagination. You expect anything from that dhan and that dhan will give you. So that means if you can develop a variety, see today is Punjab 8 tons, 10 tons, but if the variety potential is say 15 tons, so then again that gap will come. But today's varieties probably, as you said, irrigated, of course we are reaching, but then several other harsh environment, there is very long yield gap. You please write down your questions, which can be asked at the end of all these panelists. Dr. Agrawal, in continuation of that question, the question for you is, what is the possible scope for addressing regional yield gap in rice?
Thank you, sir. I'll talk this answer in a wider spectrum. When you talk of yield gap, regional or otherwise per se, it is 3-4 major components. One is genetic component, production component, input component, and taking the technology to farmer. It has some other components. So when you talk of genetic component, you develop varieties for different regions. Regions can be within a country or between the countries or between the mega system. And there are gaps, of course, that may be because of climate or agroecologies. And when you talk about production technologies, again, every region has a different situation. And there is a difference also. Punjab, for example, rice, you get 9-10 tons now also. PR 116, 117, there are 2-3 varieties. Today also they give 8 tons plus in farmers field. So, but coastal Odisha and western Odisha, again, there is a huge difference. Because maybe clouds or maybe low sunlight or there are a lot of factors. So there is a big potential to bridge the gap. And then input. In India, input, right cost of input, availability of input, and investment for production. Everything has a role. Everything can be expanded a lot. One more thing I'll add before going for biodiversity. And that is one point probably we're discussing when we discuss about the title of the conference. That I want to put it for the thought of the audience and all of us. In the last 200 years, every 50 years or 30 years, a serious research in one field has make a spillover of effect on the other field. 20th century, first half, last 50 years, there is a lot of development in physics and to some extent chemistry. A lot of Nobel Prize went to physics chemistry. And second part of the last century, a lot of Nobel Prize went for biological research. And if you see that, the effect of physical science came to biological science. Similarly, last 20-30 years, computing, a lot of things were there. AI became, and IoT became a reality. Sensor application, sensor were developed. And sir, just for the knowledge, I'm telling, 2014, first time when PMO told us that how sensor can be used in Indian agriculture, we had a series of workshops. And first workshop we conducted with the chairman CEO, Dr. Chidambaram, the PSA to Prime Minister of India. And that is probably a serious business started for sensor in ICR. And that spillover today, we are seeing drone, these, that, many things. So one thing I want to impress, the yield gap or the potential. The other development of other branches of science, what is happening today, like nanoscience, for example. 20 years back, we never thought nanoscience will directly roll in agriculture. It was, though some people may be thinking academically, but as an organization, as a planning, it was not there. But last 8 or 10 years, you see, most of the research in nanoscience was graphene or single layer graphene, nano layer, like that. Nobody took seriously agriculture will have nano revolution one day. But today we are talking that. So my point, one of the point I'm diverting a little bit, maybe I'm justifying. One of the things we have to understand, a lot of genetic research in maize had an effect in rice. Rice research has made effect on a lot of other crops, pulses, oilseed, a lot of things. So that also I feel the regional gap when you talk across the globally or within India, Genetic gap, you say rice or other crops of rice and region, the cross-lining of things has to come. The second point given to me, I'll add one sentence, I'll close. Maybe next round I can answer. Lot of people say that modern agriculture has made germplasm or diversity reduce. Believe me, as a researcher, we have every right to say it is not correct at all. Because you imagine, you want to grow 5 times the production of rice or any other crop for the 140 crores people. Probably today, no wild rice or no other crop would have been there. So by having 20% less land or 10% less land and going 5 times, we are giving scope and land for wild variety, all diversity to maintain to some extent. Second, all modern variety, you make a crossbreeding, you have a lot of all wide relatives, and you having there also harbor of genes which would have been otherwise wiped out. Last sentence, last 2 sentences, I'm counting number sentence. And third sentence and fourth sentence are, we are conserving a lot of wild rices in situ, ex situ. Also, we are having a lot of mechanism to see that they are not wiped out. It may be your gene bank somewhere. So our totality, we are responsible scientists in the country who have seen that diversity is not reduced, looking to the quantum of requirement of food and other requirements. Thank you very much.
Thank you, Dr. Agrawal. Very good. For the general audience, India is a rather questioned in many ways and also criticized that in India we have got a very large yield gap. And in every other ministry, including Ministry in Agriculture, they say that say for example, rice, they take the highest average yield of the country, highest one, and then average yield of India. So the gap is really very high. Highest average yield, say maybe some country like Egypt, average is around 8 or 10 tons per hectare. And then in our country, it is, if you take paddy also 3.9 or 4. So they question that, okay, this much gap is there. But you all understand our situations. We have got yield from less than 1 ton to 8 tons, 9 tons, sometimes even 10 tons. So all these complexities are there. Dr. Agrawal will come back to you in the next round. Now, Dr. Sundaram, a very specific question has been given to you. And the question is, how equipped are Indian laboratories as of date to harness the benefit of genome editing? Can it address the quantum jump in productivity? Dr. Sundaram.
Thank you, sir. I will answer the second question first. The question is, can genome editing address the quantum jump in productivity? I would say with double confidence that yes. As you understand, genome editing is a precision breeding tool which can bring in specific changes, very targeted changes in the shortest possible time. And we have seen, like my institute is also working on genome editing related to 2-3 traits. And with funding support from ICR, we have developed a genome edited line of Samba Masuri, which Dr. Pradhan mentioned, which has editing in GN1A gene, and which has got at least 40% more number of grains with a shorter duration and then stronger stem. So I'm sure that it can lead to a quantum jump in productivity. Why I'm saying so? Because rice crop is very unique in the sense that we have got, as on date, 5,700 genomes already sequenced. And most of our popularly cultivated varieties or parental lines have also been sequenced. And genome editing works only in those cases wherein genome sequence is available. And there is a tremendous improvement in the progress of genome editing technology in terms of enhancing its scope and specificity. Particularly in recent years, there's a lot of development, even in tools like base editing, prime editing, and also more efficient nucleases. Genome editing as a tool can improve several traits of relevance in rice, like yield and nutritional quality improvement, biotic and abiotic stress tolerance, and also improvement in grain quality, resource use efficiency. And many of these traits are relevant to the challenges faced in rice. And it is also very important that not only in rice, but in crops like oil seeds and pulses, this can play a very major role in terms of transforming the productivity and then giving a quantum jump. And I would say with confidence that genome editing technologies can transform agriculture, not only in rice, but also in other crops, as they are in perfect alignment with government goals like more crop per drop, improving carbon credits, reducing greenhouse gas emissions, and then sustainable development. Now coming to the first question, whether our labs are equipped or not. My answer is partially yes. While some of the labs like ICR, NRRA, my own institute, then NAPGR, then NABI are all equipped, very well equipped, and then they have developed products and which are ready for field testing. But to my understanding, the investments are not sufficient. Take the case of China. They invested more than $10 million in this technology, which is, for example, USA has also invested more than $3 million or either 3 billion or 10 billion. And our country's investment is a pittance as compared to these investments made by other countries. And in this regard, I'm sure that with the right investment in infrastructure, capacity building, and also the other tools which are required for genome editing, our country can also march in the right direction. And in this regard, now that genome editing is literally out of the purview of regulation or biosafety considerations, I'm sure that Indian government will also make the right investments. In this regard, I would like to appreciate the role of ICR, wherein already for a period of 5 years, they have provided funds to the tune of more than 9 crore rupees. And recently also another 12 crore rupees has been committed for targeted genome editing in specific crops. Thank you, sir.
Thank you. Thank you very much, Dr. Sundaram. Very specifically, how much money you want?
Sir,
For your institute.
For my institute, if it has to
No,
become
no, if you just tell me the amount.
okay. Sir, we require about 2 crores
2 crores?
just for the
Done,
infrastructure.
Given. When you
Infrastructure.
are going to give us the product?
Yes, sir.
When are you going to give us the product?
So within 3 years, I'm confident about it.
2 crores for these 4-5 institutes are committed today.
Thank you.
Okay.
Sir. Thank you.
So we shall do that. Actually, this is just yesterday only, we had a meeting with our finance secretary. And this is one of the areas which have been identified to be supported in ICR's genome editing. Already in 5 institutes, the work is going on several crops. All of you are also party to that one. And then we are really going to strengthen this particular activity. I was expecting that Dr. Sundaram will be asking quite huge amount of money, but he simply asked only 2 crores, which is already very easy to give. So Dr. Sundaram, you are going to get this money. Okay, very good. Thank you very much. Friends, we have got Dr. Johar Ali, who has joined online. Dr. Johar Ali, am I audible?
Yeah, I can hear you. Yeah.
Thank you.
Please
Thank
go
you, Dr. Johar Ali. So welcome for this second Indian Rice Congress. And the question which has been posed to you is, despite 30 years of research on rice hybrids, their adoption rate is abysmal in our country. What is the way out? Over to Dr. Johar Ali.
Yeah, thank you. So actually the key factor or the key driver for any technology to adopt is the yield as far as rice is concerned. And hybrids have to be highly heterotic as compared to the check-in breeds with more than 30% at least to attract the farmers with increased stability. And in this direction, we need really to have genomic selection tools within the heterotic pools in order to maximize the new combinations that we are attempting. And again, the 2-line hybrids, since there is no restoration there, the entire gene pool of rice is opened for it. And therefore, the heterosis can go beyond 30% even. And it is largely, it has to go through market-driven approaches rather than not blindly doing some trades here and there, but it has to be driven through based on the market requirements. And basically, we have not been systematically improving the GCA of the parental lines and very less focus on the hybrid seed reproducibility. That means if you don't target about 3 tons per hectare for any hybrid that would be released, that should be a yardstick in the future so that these type of levels of seed reproducibility of an hybrid would allow the private sector to invest into the technology itself and make sure they get enough return on investment. Previously, people used to say that the hybrids are susceptible to insect pests and diseases, but this is a thing of the past. When you have multi-stress breeding of ideal parental lines, we can match them and complement them in both the parents for many of the biotic and abiotic stresses. Another important factor why it was not adopted very seriously is because of the grain and cooking quality. if you remember the F2, what we eat is basically an the hybrid that we eat is F2, basically when it's on your plate. So we need to really make sure that the hybrid that we want for a given market, it has to match that grain quality requirements. And above that, the high head rise recovery should be a standard for hybrids to be even released. So for example, recently we got hybrids that can cross even 60% head rise recovery, and milling recovery should be more than 70% with less chalkiness. So this is attracting the attention of the millers, and the grain quality or the cooking quality should match what the consumers prefer. And then if we really want the latest state of genomics, the informatics, and how we really exploit the genomic prediction tools and artificial intelligence, you need not do large number of crosses to make them. By such technologies, we can easily zero in to the most heterotic combinations within what we have. And this way we can increase the efficiency and predict these crosses way ahead. And that's how I look at it. And at this point, the hybridized seed reproducibility is a very key factor. And IRI is also trying to bring in the high outcrossing traits into this. And this is possible. And lastly, I would, as you mentioned about the funding, unless we don't fund this type of research to the public sector within the country, in fact, this has to trigger the product development and then give it to the private sector to make the last run, to make the hybrids at a cheaper cost, and make sure that we reach to the farmers at the most efficient and most productive way. Thank you. Yeah.
Thank you. Thank you very much, Dr. Joharali, for giving a very optimistic view of hybrid rice. Friends, आपको तालियां बजाना पड़ेगा बीच-बीच में at least, so that they get a little bit more energy, to speak more about it. So, Dr. Saab, thank you very much. Now let's come to Dr. A.K. Nayak, who is always posed difficult questions. Dr. Nayak, the question given to you is, to what extent rice-based farming can be brought under natural farming, and what should be the roadmap to follow? Dr. Nayak.
Though it is a difficult question, I will give simple answer. Before discovery of a chemical fertilizer, all the agriculture which were practiced in this country and abroad were some kind of natural farming or organic farming. The question is, after the advent of chemical fertilizer, we are coming, it is a chemical farming. So as on today, if you see the pattern of fertilizer used in rice farming, still we will having area around 2 to 5% area where no fertilizer used at all in rice farming, because that ecosystem does not provide an opportunity to the farmers to apply fertilizer. So, and there are area where 20% of the recommended fertilizer, if you take Odisha into consideration, the per hectare NPK use is around 65 kg NPK per hectare. But if you compare with for Punjab, it is 150 to 180 kg per hectare. So this is such a wide variations in terms of fertilizer use. And the same is in terms of your pesticide use, the special distribution. So that means in some areas still we do have, which is under some kind of natural farming. The second aspect is the concept and the definition of natural farming is so heterogeneous. It's some kind of zero budget natural farming, rishi kheti, paramparagat kheti. So that when we are discussing in a scientific field, there must be a reconciliation of the definition. The first is, unless we reconcile, we cannot transact our business. And the question is, again, we should not treat the natural farming in isolation. So no modern science can be developed in isolation without taking cues for other branch of science. So natural farming also, if it is a branch of agricultural science, so other branch of scientific development should be infused. But some of the purists which do tell in our tradition, our rishis, maharshis, they were doing this kind of khetis, and we will only do that kind of agriculture. We will not imbibe the modern principle of agriculture and other branch of science, whatever development is taking place. Also, to my assessment, we need not so purist with respect to the definition and concept of natural farming. Then the third aspect is it should be evidence and data-based kind of policy decision. Of course, Indian Council of Agriculture Research has asked all its KVK and ICAR Institute to have a demonstration plot on the basis of which data can be generated, and future, if any policy decision is further pursued, so it should be evidence-based kind of thing. But coming to the very essence, the question, the idea behind this question is how we will carry forward, what is the way ahead. The way ahead is, of course, the natural farming tells that exploiting the microbial and biological resources that is present in the soil. 2% of our microbial resources is culturable, rest are uncculturable. So we do not know the tremendous potential which exists beyond our known of our microbial scientists. So how, without any interventions, we can get the synergy of this biological system and get higher yield, take integration of animal husbandry, tree and crop. So that is a branch of science. It is evolving. I think we need to generate data, and we should again reconcile the definitions. Third thing is, when we are exercising developing course curriculum, I think recently we have done this. While doing this also, there were so many discussions whether some aspect of course curricula in natural farming should be borrowed from other branch of sciences or not. So there was a discussion. So it should be open-ended. If at all there is some synergy that natural farming can get from other branch of science, we should not be so purist. And while developing course curriculum, we should also take in the modern development of instrumentation and modern principle of science that also need to be imbibed in case of natural farming. And if we, those things are taken, the ultimate objective is to enhance the productivity without hampering the ecosystem service or the productivity of the system. So that can be done by reconciling some of our traditional principles, which was driving earlier civilization, and the chemical discoveries. Before few years, we are having the chemical discovery. Before that, many civilizations were run by this natural farming. So those principles need to be assimilated in the modern science to get best benefit out of it. And currently, those natural, the farmers, those who are practicing natural farming, we should supplement their income through some kind of ecosystem service. I think these are my questions to this difficult answer to the difficult question.
Very good points. So you said that it is possible, but then there are several other things we should be open. And of course, at the end, I shall request Dr. Agrawal, who is the architect of the whole course on natural farming. You know, in ICAR, we are working at 3 levels rather. One is, of course, developing course curricula and so on. Second one is 425 Krishi Vigyan Kendras out of 731 now are having demonstration as well as training and those things on natural farming. And the third one, which you said that 21 of our ICAR institutes are now conducting experiments on natural farming to generate data, because science is basically data. If it can be supported by scientific data, then only the thing is going to be survived. So thank you, Dr. Naik. We may come back you again in the second round. Now we come to Dr. Birender, and of course, all of you know him. Dr. Birender, the question for you is, what are the barriers and drivers of direct-seeded rice for adoption by small and marginal farmers?
Thank you, sir. So I'll start with the first drivers, I guess. And I think most of us know the drivers. It's very easy to answer. So I think the drivers depend on the stakeholders. And I would say for farmer, the major driver is labor scarcity. And we know the labor is so difficult to find. The quality of labor is another issue. So labor is the biggest driver. And we have seen, we witnessed that during COVID time, because of labor scarcity during COVID time in Punjab, Haryana, the adoption of DSR happened very quickly. We were trying DSR from last so many years, just COVID, labor scarcity, and boom, right? So that's the major driver for farmer. Second is water scarcity. And Dr. Khush also mentioned about the water issue, particularly in Northwest, where the water table is declining at like a 0.5 meter per year or even 1 meter per year in some location. So that's another issue. Third, I would say from farmer perspective, also the economics is very, very critical because the cost of production is increasing. And so farmers are looking for any practices which can reduce their cost of cultivation, and direct seeding can help in that. And fourth, I would say climate change, in terms of adaptation to climate change, mitigation to climate change. That's the interest of scientists. We are looking forward any technology which can reduce greenhouse gas emission as well as can adapt better to climate change condition. And finally, I would say that the increased interest of private sector in this technology, and primarily because of this emerging carbon credit or carbon market. So there's a lot of interest from private sector, and when private sectors are involved, I think there's always push, faster push for DSR. So these are the major drivers, I would say. Now question comes to the barriers. And again, I'll first talk about the technical issues and then non-technical issues. So first is, I think it's very, very important, the uniform and good crop establishment. When you see transplanted rice, it's assured crop establishment because you're transplanting. So for any crop, if crop is established very well, 50% of your work is done. But major risk in DSR is achieving good crop establishment. The many factors could be land leveling, could be machinery issue, if precision machinery is there or not there, seeding issue, and also another issue is this rainfall. If field get flooded around crop establishment stage, inundated, I think rice is sensitive to flooding at germination stage. Once established, it can tolerate flooding, but early stage is very, very critical. So if field get affected, field get inundated, then crop establishment will be affected. So achieving a good crop establishment, a lot of progress has been made. I can discuss later, but that's one issue. A second, I think, is weed management. So this is also critical. I mean, as we shift from transplant to direct seeding, so the weed become issue because weeds are emerging with the crop, whereas in transplanting, you already have 30 days advantage. So crop has a head start. Second is that you can flood the field in transplant rice, whereas in DSR, you cannot flood immediately. You have to wait till it's established. By the time weeds are already established. And then because of no flooding, there are a lot of difficult to control weed starts emerging. So this is a challenge. I mean, weed control is a really challenge. A lot of progress has been made. Options are there. I think the major issue is the knowledge, how we convey this knowledge to the farmers, because weed management has become knowledge intensive. So we have to develop a tool for farmers which can help them to select the right weed management option. Next, I think, is variety. So currently we are using variety which has been bred for transplanted system, but I think we need a dedicated breeding program which are variety breeding specifically bred for DSR condition. And I'm happy that a lot of organizations are now working on that. And we recently just this year a project has been approved from BMGF for India for especially for breeding variety for DSR condition. And then I'll come to some, I mean, of course, the other technical issues are more nematodes and all those issues. But I think non-technical, I think is a very, very important is awareness. Still, I think demonstrating at farmer field that this technology works at scale. So that I think really cluster demonstration, large scale demonstration, where we can demonstrate that this technology can give similar yield at least or higher yield. That's one thing. Also capacity of the extension worker working in the field. I think we have to increase their skill set so that confidently they can go to the field and demonstrate the technology. And I think I'll stop here. I think, yeah, thank you.
Good, thank you, Dr. Birender. So you said there are drivers and there are also barriers. So at the end, who wins, drivers or barriers, that we have to see. But then there is a lot of scope, as you very rightly said. So thank you very much. Now let's go to the last panelist of this session, Dr. Mohanty. Dr. Mohanty, am I audible to you?
Yes, Dr. Pathak, yes. Can you hear me?
So Dr. Mohanty, welcome for this exciting discussion. The question to you is, how feasible is smart or precision farming for widespread adoption by small and marginal farmers? Dr. Mohanty, over to you, please.
Yes, thank you, Dr. Pathak, and thank you everybody, particularly the organizer, for inviting me. Let me before that, before I answer the question, I would actually like to put a question to the audience here. How many feasible technologies, actually the digital tools are actually available that works at the field level? before we talk about the adoption of the farmers, do we have digital tool that really works at the farmers level? Particularly, let's talk about the site-specific nutrient management. I did some randomized control trial in Philippines when I was there at IRI. And our final conclusion was that the SSNM, the people who practiced SSNM and who did not, really there is no significant yield difference there. And most of the farmers did not actually follow the recommendation we sent them by mobile tool there. Let's assume that smart agriculture is obsolete. No, absolutely. I think the smart agriculture is the future. Eventually, it will be adopted by the farmer. There are several constraints there. Let me identify 5 key constraints right now. What is stopping farmers adopting some actual digital tool that is working at the field level? There's very small land size. You all know that. They're all dispersed, millions of smallholders. They're dispersed all over the land there. The technology cost, high cost of the technology itself is also a big hindrance there. Then technology operation related difficulties farmers face. Smallholders really cannot adopt technology which is very complex, difficult to operate there. A lack of support to the farmers there. Farmers are there on their own. Who is going to provide them the support on the digital tools, all the nutrient management recommendation tool you have provided? So there is no professional support available to them. Then the lack of supporting policy enablers, we call it enabling policies, also stopping the adoption of this smart agriculture there. Are there any solutions there? Of course, there are definite solutions there. Let me give you one example. The smallholders are dispersed. They are facing diseconomies of scale. They're facing lack of bargaining power in the market there. So if we address some of these things, particularly through some collective action approach, for example, FPOs, some of these cooperatives, I actually implement one bottoms of collective action approach called small farmer large field in Odisha. Right now, the 20,000 potato farmers are implementing that. Basically, they work together, they come together when there is economies of scale they have to achieve. Like, for example, joint seed purchase in potato, nursery development, nursery establishment in rice. So similarly, the collective action approach, if we have more and more, they are out there, where the farmers are doing it together in some form or the other. It could be formally, FPOs could be informally there as a group, small, self-help group, other things there. It's easier to reach those farmers and convince them to take up a digital tool there. So it's very important that collective action eventually should help farmers, smallholders adopt the smart agriculture, any sort of digital tool there. Low cost of technology. The technology has to be very low cost or actually free in a sense for the farmers. From the farmer's perspective, it should be completely free. The developers should collect the money from somewhere else, not from the farmers there. It's very important that it should not cost anything to the farmers. Education to the farmers. Smallholders, they need to be educated in terms of the technology itself, digital tools, other things there. Service providers. Eventually, I think there has to be somebody in between the technology developer and the smallholders, which is called service provider or anybody in between who can help them, adopt this technology, provide that necessary support, provide that technical know-how. Any sort of difficulty they face, they overcome that there. Then the final is the policy initiative, any sort of policy that supports, that encourages the development of technology, that encourages the service providers to emerge and support the group of the smallholders there. But if we address all the constraints, we have all the solutions there. But again, my question comes back to how many feasible digital tools you have that really works at the field level. If you talk about the site-specific nutrient management, any sort of input use tools, that's probably one of the things very popularly developed by many agencies there. Do the developer really can put their money and say that farmers, here is the tool, and here's the recommendation you follow based on the mobile application I have. But if your yield is less than the guy who is not using, I will compensate. Can the developer guarantee that? If not, then the farmers say, how can we expect the farmers to adopt a tool so we are not confident about that? So I think eventually there will be technology. I think eventually there will be digital tools, simple, inexpensive, and which will be adopted by the farmers, because that is the call of the time, that's the need of the time, and it will happen over the time there. Thank you.
Thank you very much, Dr. Mahanti. Very nice, yes. Of course, these two sides sometimes meet, sometimes do not. So technologists feel that they have got technologies, then social scientists feel no, there are several constraints, there are several barriers, there are several limitations. But I'm sure at some point in time we have to converge. Then only we'll be able to progress further. Friends, with this we come to the end of the first round of our discussion. Now we shall move to the second round. You know, the questions, I really like those questions, whosoever has said, maybe Ratnak and maybe others. But then let me also tell, the question setters are very liberal and generous. They've given hints also that what you have to answer. And the questions are out anyway, so they know it. But then very pertinent questions, and then what the response we are getting also very, very useful. Let me tell you, this very, very learning experience for all of us. So in the second round, friends, we shall again start from Dr. Pradhan. And Dr. Pradhan, the question for the second round to you is, what should be the future roadmap to enhance rice productivity under changing climatic scenarios? Dr. Pradhan, please.
Yeah, thank you, sir. This topic I will be, sir, speaking tomorrow morning, about 30 to 40 minutes in my
but then you have to tell it today in 2
lead
minutes.
lecture. So within 5 minutes,
Yeah.
I will be trying to justifying this. So I will be starting from classical breeding via marker assisted breeding to the recent one, that is genomic assisted breeding. So the roadmap actually, you know, everybody, classical breeding, yeah, conventional breeding, we achieved the success. And the green revolution, food sufficiency, whatever, we achieved that. But then where is the problem? Problem is that we have to take a large number of progeny, and then we have to select. Number is very important, as well as undesirable effects are coming. To eradicate that, we are taking large number of progeny. For example, I am telling you, for 5 to 6 genes, we are taking as many as population like 2,000 more than that for getting one homozygote plant. So in order to achieve that, it is that's why we have to give more resources, and the selection is based on the phenotype only. So in order to go for higher precision and efficiency, then our next is our marker assisted breeding, where the plant, yeah, the target trait is a single trait, yeah, single gene, where we can introduce few one like 2, 3, 4 like that through marker assisted breeding. We can introduce using the marker. So in that case also 4, 5, 6, I told you about more than 2,000, 3,000 progeny we have to genotype and phenotype. Then only superior one we are getting one only. So you can consider in case of 10 genes, 15 genes, 20 genes, what will be the population size? It will be huge, maybe in lakh. So is it possible to genotype? Is it possible to phenotype? So that is the success. That is a success one marker assisted breeding. Few genes we can introduce. For example, disease resistance. Yeah, any trait which is having gene having clear cut phenotype, we based on the marker we can select that plant. But in case of this, what is given to me, it is for climate resilience. You know, for rain-fed ecology, so many traits are there. So many biotic stresses, trait tolerance stresses like drought. It is governing almost 20, 30 genes, then submergence, then salinity, then bacterial blight, then blast. If in that way you will be considering, you will be taking to get a SIRC, what was telling, I was also having that concept, to end up with a smart version, a resilient type one. We need large number of genes to be put together, again with less resources, with using very small population size. So this is possible using the genomic assisted breeding. Instead of marker assisted clear-cut background, we have to go genomic assisted breeding. Here, large number of QTLs based, the selection will not be based on a single gene or few gene. You have to see here the holistic effect, all the genotype. What is the breeding value of the genotype, individual genotype, and how to get that? That is based on model based. You have to use a perfectly breeding model, means bioinformatics model. There are many models, and using a chip based marker, yeah, QTL's effect, you have to estimate the breeding value of the individual, yeah, progeny. So in that way, it is a totally bioinformatic based and breeding biotechnology in combination. That is genomic assisted breeding. And you will be at the end, you will be able to estimate the breeding value, individual breeding value, using less progeny, less number of cases, as it started initially in case of animal breeding. But due to the success of that, in case of animal, you know, the progeny number are very less number of progeny they used to use, and they used to get very good result, precision result. So that concept can actually, we started in case of plant, and that genomic assisted now we are doing in case of rice, and yet we are not getting any publication in rice particularly. It is successful in maize, in wheat, in canola, but now we have started in case of rice also. So I hope this future of rice is genomic assisted breeding. Here what you have to do, you have to select whole the genome, the genes, what are the genes effect through chip based. And all these you have to go in a cycle way, that is different cycle. As you know, the breeder's equation is two things, these are dependent. One is heritability.
Dr. Pradhan, you have to conclude now.
Certainly, first round I have taken 1 to 2 minutes.
Okay.
So I will take 7. You know, this is a longer one.
Go ahead.
So, sir, here, that's why I used to tell that all the cycle we have to select in a cycle manner, and each cycle we have to see the breeding value, that is training population and breeding population. So initially we have to take such a training population where all the traits, like 200, 300 traits to be taken together, and in a cyclic manner, we have to put together all these traits at the end will be recycled into one progeny. That is the power of genomic assisted breeding. So if it is a successful one, then only we will be getting a climate resilient version. And that is the future roadmap, future. Tomorrow I will be presenting that one. Thank you, sir.
Thank you very much, Dr. Pradhan. Very good. Very good. आप दोनों मिला करके भी 1 minute तब भी कम है. So you can take 1 more minute actually. But anyway, thank you very much. Now let's go to Dr. Agrawal. And Dr. Agrawal, very pointed question to you. Is agricultural biodiversity at stake?
Sir, already
Due to the wiping out of traditional varieties and land races in modern day high input.
Sir, already I touched that point. If you allow me,
Yes.
I'll use the other point. I'll cross panel, supplement, complement, I'll do, sir.
Yeah.
That is also scope.
No,
is there.
you stick to your points only. We shall come to the end at the
Sir,
cross one.
second round, it is written, sir. You can do.
Go ahead.
So let me do that.
Go ahead.
Because that will open some discussion. So one point, genome editing, Dr. Sundaram talked one sentence, genome sequence should be available. Truly speaking, target gene, if sequence is available, that should be enough. You don't need a genome sequence for the whole genome. Absolutely not required. So that should be fine. Second, the hybrid program I saw, it was observed that heterotic pool. One of the best example to understand is maize. And if you see the history of maize, lot of known heterotic pools are there, and inbred performance over years is improved. Even we have seen for hill agriculture, I had occasion to work in maize for many years. The inbred for 90-day duration crop in maize, maybe 3 ton, 4 ton inbreds were there, and over time we got 6 ton plus inbred capability. And that is why we had 10 ton plus hybrid with 90-95 days crop. So there was so when you take the experience of heterotic pool only, a non-heterotic pool in rice, I don't know how much we are having or not. Maize, it is very well worked out. but some of the experience of maize-like crop or horse. Horse is a very good example where heterotic pull has worked very well. So maybe rice, I do not know how we have taken the experience of that. Third, the natural farming, organic farming. That is a critical issue everywhere discussing. Let me share experience we have done. We did an exhaustive experience because till modern breeding, we are using all breeding were in inorganic condition. We are putting fertilizer and we are making selection, and we are seeing these varieties fit for inorganic condition. So we wanted to test whether modern day breed varieties, can it work for organic conditions? And we did exhaustive work in Almora when I was there. And we took a variety Vivek QPM9, that was a flag project because that is the first biofortified crop released from ICAR or India also. And we saw that if you calculate NPK and put for organic input accordingly, you can get yield as good as or more than what you are doing in organic way. We got almost 10 ton plus in VQPM9. And that is one of the examples. And we sort out a lot of varieties we can do well. So from that, our experience, we say available variety, you can identify some variety which are good for natural organic condition. And that is one of the experience will answer a lot of questions by a lot of people. One of the questions Dr. Mahanti was talking and other things, sensor business. Today, we have low-cost sensor for many things, which are right now works in farmer's field. One of them is water sensor. With 500, 600, 700 rupees, you can buy a sensor, put in field, and put an IoT model, and your mobile can switch on and switch off the mobile phone. If you use it, at least 30% water you can save using a sensor, which is very easily applicable. Tomorrow we have a speaker. You will like to listen. Of course, you will talk for rice, but is Apple experience I'm telling. NSF, we had funded a project, so I know more detail. You can rightly harvest an apple or some other crops right time, pre or post harvest to make a lot of effect. And the sensor costs hardly 500 to 700 rupees. And Kashmir CITH experience says it was perfectly fine. So today sensor is more acceptable. Last, if you allow me, last one point I'll say, sir. Otherwise, I
shall come back to you. Don't worry.
Okay, then let me. Then
we have got the whole night.
Yeah. Thank you. Thank you.
We'll go on discussing and discussing. Okay, friends. Again, clapping is missing here. So we shall go to Dr. Sundaram. Dr. Sundaram, again, a very pinpointed question for you. Can biofertilized rice carve out a niche in the already established sphere of chemically or externally fortified rice grains to address the problem of malnutrition and, of course, undernourishment in India?
It's an easier question, I would say. I'm very confident that biofortified rice has a key role to play, but it's not the only tool. It's one of the tools to minimize or address the problem of malnutrition. And we are talking from our own example, wherein my institute is coordinating a network called Consortium Research Platform on Biofortification, wherein 5 crops are addressed for various nutrition-related traits. In rice, we are working on improving the protein content, iron and zinc content, and also improvement of few essential vitamins. So in this regard, already a very good product, which was already mentioned by Honorable Minister, called CR-310 has been developed. And it has also been, I understand that it has been licensed to a few companies. And same case with IARR, we developed 4 high zinc rice varieties. DRR 45, 48, 49, and then 63. At least 2 of them have been already licensed to private companies. And the response is very, very good because they are there in the premium grain segment, either long slender or medium slender. And the people who are licensed it also very happy. And I would also like to say that for the past 2 years, in collaboration with ICMR, National Institute of Nutrition, we have been carrying out feeding trials to Anganwadi school children in a few districts of Telangana. And this has been very highly successful. And we have seen clear-cut results in terms of improvement of health attributes among those children. And this was very well appreciated by Telangana government also. Now, pitching in biofortification versus chemical or external fortification, there are always certain limitations in chemical fortification. For example, may involve initial investment for blending plants. It may have some problems related to storage, and it may also have price-related issues and also issues related to delivery, product delivery. All these problems are more or less very, very minimal in case of biofortification because it's a one-time investment. Once you produce a biofortified rice variety, it is a sustainable approach so that farmers can grow it again and again, provided they use proper seed, and you need not invest it year after year, while other approaches need constant investment. Now coming to the last issue, I've been asked relevance of biofortified rice to the well-nourished section of the population. As per our program, biofortified rice is mainly targeted to the weaker sections of the society, which suffer from protein energy malnutrition and also micronutrient deficiency and other deficiencies. But there are a few biofortification related traits like high oryzanol bran oil or improved brand quality, low GI rice. These are even relevant to overnourished or people in the urban areas who may not require a zinc fortified rice, but they may require these sort of traits. I think it is also relevant to some extent to the well-nourished sections of the population. I end my case here, sir, but I have a few questions to some of our panelists. Sir, to Dr. Pradhan, my question is, with regard to genomics assisted breeding, there are multiple approaches. One of it is backcross breeding.
Can we do it like this?
Okay.
Keep your question.
Okay.
So once this round is over, then we shall come back to everyone's question, including audience question.
Yeah. Thank you, sir.
Okay.
I make this.
But I shall pose one question to you.
Yes, sir.
Of course, biofortification has got several advantages, but then why we could not convince the government, and government went for external fortification? They made it a policy for external fortification. They didn't make it a policy for biofortification. We shall come back to you, not in the next round. Okay, so now let's go to our next. Yes, that's good. Now let's go to our next panelist, and he is Dr. Johar Ali again. Dr. Johar Ali, the question to you is, what is the way out to overcome bottlenecks in research, collaboration, and material transfer in hybrid rice? Dr. Johar Ali.
Yeah, it's a very good question. Just to highlight the collaboration itself on HRDC, for example, the HRDC was formed as early as 2008, but ICR joins HRDC in 2019, almost 10 years later, and lost a lot of this momentum on hybrid rice. So in 2019, we made it very seriously. We took it very seriously and put ICR at the highest level of platinum green member. And by 2020-21, we have already shipped all the seeds that were ever shared with the other HRDC members from that era, which ICR missed completely. So there is a huge volume of materials, both female parents and the A line, B line, and R lines have been shared. And this will put already IIR and IARI and NRRI in a very strong footing to develop the new hybrids out of them. They are very highly potential hybrids, can be developed, and we are also sharing the hybrids also. Now, one of the key constraints which I looked at how we can really achieve that momentum is basically, for example, now NBPGR allows only 200 grams of testing per hybrid. It allows, if you have to send to India, only 200 grams of hybrid I can send. So we request under your leadership, for testing of hybrids, at least 1.5 kg, then we can at least test in 20-30 sites. And then some reasonable information can come back, and we can really fine tune which parents are working and where they are working, which geographies are working. And then we have one NARIS network testing, which is recently happening, which is about 134 sites across the globe. At least for India, it should be around 35 or 40 sites. We can leverage this testing site if we get the opportunity to ship more quantity of seed for a given hybrid. And then in the One NARIS network, recently IRI and ICR institutions and the SAUs have already joined hands. And we are first time going to test the stage 1 and stage 2 hybrids in comparison with inbreds in all the rice breeding or market segments that we are addressing. So there will be head-to-head competition between inbred and hybrid. For those people who have still doubts in their mind that the hybrids are really good or bad, they will come to know directly. So that would really encourage the SAUs and the institutions who are looking at the hybrids. They will see the performance of the hybrids against the inbreds, and that would trigger the excitement in the research circles. And then the two-line study group materials are which we will bring to India, which already is with the private sector. 5 private sector, they have demonstrated in the last 3 years that they are doing very well. So we have already going to make sure that this technology prevails in India very soon. And also IRI and ICR have very good relationship going forward, especially for hybridized, because we are also initiating co-hybrid development with IIR and other institutions who are interested, co-development of parental lines even, so that we can share the licenses of IRI hybrids with the IRI ICR NARES partners, with the private sector collectively. And this way, I see there could be a lot of this research collaboration and easy material transfer agreements. So recently in 2017 or 18, we introduced the RETA, which is called Restricted Evaluation and Testing Agreement. Under this, actually previously before 2016, there was no way we can even share the hybrids to other partners. So after this introduction of RETA, this allowed openly allowed IRI to test large-scale testing of IRI hybrids in different countries. And this is a very simple test. That means after F1, people will not breed through these materials and rather test them and evaluate and return back that information so that we can provide the parents and the right thing through licensing approaches, so that all the players in that stakeholders win the game. And recently, we are also going to organize one-day workshop exactly to understand why there was slowdown of the hybrid technology in India for last several years. We are seeing it's stagnant around 3.5 to 4 million hectares. And by this way, we cannot go forward, because during the climate change, the only technology that would prevail would be the hybrid technology with 30% yield advantages. Could be a very significant way to defend the productivity and production of the country from this climate change things. So this will be discussed in a one-day workshop with IRI ICR collaboration. We are going to organize soon and try to understand collectively with all the stakeholders why that stagnation was there, and try to bring out solutions and collectively address this in a very organized manner. Yeah, that's it. Thank you.
Thank you, Dr. Jarali. Thank you very much. These are very pertinent points. And of course, in our forthcoming IRI ICR joint meeting, we are going to discuss it. Dr. Pradhan, you can also put some of these things, including quantity of seed, whether that can be increased and so on. So some of these practical issues can be discussed, and then we can take a decision. So thank you, Dr. Jarali. Let's again come back to Dr. Nayak. Dr. Nayak, in this round, the question is, can we give a realistic timeline for net zero emission from agriculture in general and rice-based farming in particular?
Thank you, sir. As India has already given a timeline, by 2070, we will be achieving net zero emission from our economy. So once we do have some kind of target for whole economy, agriculture must be having some kind of a target when we'll be achieving net zero emission from agriculture. So the question is, irrespective of whether it is realistic or not realistic, we must be having some target that motivate us to streamline our research policies and efforts to meet the targets. So at least if we, from agriculture, from ICAR side, if we can give 2047 is the 100 years of our independence, by that time agriculture, we can achieve net zero emission from agriculture. And if we can split it, crop and animal husbandry sector, the crop sector we can achieve much earlier. And the whole agriculture, if you take into consideration, we can keep it 2047. Of course, whether irrespective of it is realistic or unrealistic, and we should put a target to coincide with some historical date. Coming to the technological aspect through which we can get this target, the existing technology which we are having, if we can simply upscale it with respect to your DSR, alternate weighting drying, combining alternative weighting drying, conservation agriculture, restorative agriculture, integrated nutrient management. These things and crop diversification. So they are having potential for 10 to 15% reduction in GHG emission to even 60% GHG, 70% GHG emission reduction. So simply upscaling, we can reduce substantial amount of your emission. And whereas 2022 energy bill in India that has given open up opportunity for carbon farming. So even some of multinational company, they are coming in a big way, particularly Mitsubishi, Bears, they are coming in a big way. Because in the international market, there is a huge demand for this carbon credit. And they want, they are seeing some of the potential area in India, particularly they are in the initial stage, they're interested in DSR. So if they are targeting, if we have say 3 lakh hectare area, if they are going to bring your rice farming to DSR, then there, how much carbon credit is there? Some company in UK and some other country, they can purchase that. Because our energy, your bill has all opened up those carbon farming area open to our farmers. So parallelly, the emission reduction technology and carbon sequestration accrediting technology, if we can aggressively pursue, we can achieve that target fairly. Coming to the next emerging technology, some of the nano fertilizer, even the nitrogen fixation in cereals, and some microbial fertilizer development, those are technology, futuristic technology. If they can be leveraged, the timeline can be still lesser than that timeline which we are giving. I think with this, I conclude.
Good. Thank you, Dr. Nayak. Good. I think it is possible, and 2047 could be a realistic timeline, and that will be very good also. That is also because by 2047, maybe on some other occasion, I'll be discussing, of course, not today online, with all our staff, what are the aspirations of Government of India by 2047? That is in the field of agriculture. And Asia is already gearing up for those kinds of things. So maybe on one day, we shall arrange some online kind of meeting for that. So Dr. Nayak, thank you very much.
Yeah, Dr. Pathak, I would like to take 1 minute to respond to what Nayak had just mentioned. Is it okay if I just would add something what Nayak said?
Dr. Jaharali, I shall come back to you.
Okay. And I just wanted to add a comment there. That's
Yeah,
it.
of course. We shall take your comments. Not only yours, we shall take others' comment also. Let us finish these 2 more panelists. So, Dr. Birender, again, coming back to you, the second question is, again, a little critical. Despite giving incentives to diversify rice to maize and cotton in Punjab, so far it has not achieved the expected level of success. So in your opinion, what are the ways and means to upscale and outscale the crop diversification in different rice ecologies?
Thank you, sir. Very, very difficult question, no doubt. So I think it's very important to understand why it is not happening. And we should look at that holistically. We know some answer, but I think understanding from farmers' perspective is very, very critical, because should not be top down. It should be both top down and bottom up approach, what we call middle messy, because most of the time we do mostly top down and things doesn't percolate. So I think it's very, very important to understand farmers' perspective, what is not happening, and then really seriously thinking about how we can address their issues. I think based on some discussion with farmers, of course, there's a policy mismatch. If you look at Punjab, if water is free and there's assured price, particularly procurement, and then why they will switch to alternate crop. When they switch to alternate crop, there's a risk, because it's a monsoon season and climate is changing. One heavy rain event can damage the crop. And its stability is more important. Maybe in 2 years, we have good yield, but third year may be poor yield of the diversified crop. How stable yield of our options are. The risk is very, very important. Farmers don't want to take any risk. We have to give a solution to them, which at least provide them same income or higher income. So there's no way the farmer is gonna bear the cost of the new technology, right? So understanding what the issues from the farmer perspective is very, very critical, and making sure whatever option we're giving is risk-free, and then at least remunerative as good as the current crop. That's the key one. And then, of course, how we handle the policy. It's very difficult to change the policy once it's given free. So how we do that, I'll come to that point. Also, I think synthesis of what are options we have tried and what are the options within tested gives economically viable with minimum risk. That synthesis is required. I think that is still lacking. And then really looking at which option fit where. Because I think if we try maize only, it will not fit everywhere in Punjab, Haryana. There are some areas which are not suitable for maize because these are reclaimed soil. So we have to really look at this, the targeting. I mean, different options, where these options fits and which option has the lowest risk. That's another thing. Another point is, one of the reasons why farmers are not interested is because of price volatility of the crop, new crop, right? Rice and wheat is government is procuring a price, they are getting it, but the new crop is basically market price. So when the area will increase, what is the risk, the price volatility of the produce? And I think it would be very, very interesting to see if we can bring in price insurance scheme. So at least that, if there's a really, price down in the market, how we protect the farmer, So that could be looked at, and then seriously looking at how much, if you put together all the subsidy, whether it's free electricity or procurement, everything, how much we are investing in the current crops, and what would be the cost if we transition to the diversified crops, and whether is there any gap in subsidies more than what we're gonna, really for transition, the cost would be, or is less, and then how we fund that additional cost, or if it is lower cost, it's easy, right? And finally, I think really doing scaling experiment with farmers, learning from the farmers who are the early adopters, who are continuing it, and who have disadopted it, what we can learn it, and really sitting down with them and finding a solution. It's very, very critical. So, and last point, I think, is the market value chain, So all these are linked with the price volatility. If you have the market value chain is there, I think the price stability will be there. So these are interlinked issues. But for me, I think making sure, we avoid the risk, and then making sure that farmers get remuneratively equally at least or more than the current crops. Thank you.
Thank you, Dr. Birender. Very good, good points. But then we are asking you simply to diversify, and you are asking us 10 things to do. So it's 1:10. Of course, these are all realistic. These are all very, very important issues to be discussed. Thank you very much. So the last panelist in this particular round is Dr. Mohanty again. So Dr. Mohanty, the question for you is, how far does the current production system support gender equality in rice farming in India? Dr. Mohanty.
Yes, thank you, Dr. Pathak. I think this is a very, very important question, because there's not a single answer whether the current system supports, or definitely does. If you look at the data in India, particularly the land holding by female, it is on the rise. It used to be 10%, now it's close to 13% there recently. Maybe a little more recent data will show that. So that means the supports, whatever system we have, a production system is enabling women to become the land title holder there. So part of the gender equality process there. So the gender equality, when you look at it, is it good? Yes, definitely. I think the literature, there is ample evidence. Gender equality leads to more productivity, efficiency gains, and also leads to poverty reductions and all the other, So definitely we would like to achieve the gender equality in not only in rice, in agriculture in general there, because the women contribute half of the labor force in agriculture are women. In Asia, in India also, many states are more than half. In UP, more than 70% labor, in particular in agriculture, comes from the women there. And other states have varying numbers, ranges from 40-45% from Odisha to Bihar to Tamil Nadu, 55%. So it ranges on average 50, half of the labor force provided by the women there. So we definitely but if you look at the amount of the labor force given by the provider women, the land ownership, there is no match there. So you would ideally would like to have the half of the land ownership or land title is by the women there. Right now it's 13%, which is way too less in terms of achieving the gender equality there. One thing I would like to point out that there are changes happening in agriculture, not only in India, all across Asia, because of the out migration of the male members there. So who are left in the villages are the women and the elderly people there. So the more and more women who used to be just the agricultural labor in their own field, doing part of the crop establishment, weeding, the harvesting and post-harvest activities there. Now they are becoming the farm manager. There's already evidence data coming out. More than women are taking up as a manager of their own farm, because the male members are moving out of that. But the land ownership still lies with the husband, not with the wife. Wife is a manager, but all decision, everything comes to with the husband still now. The land ownership not increasing proportionately the way the women are becoming the farm manager there. So if you look at what exactly needed to accelerate the gender equality in rice and in agriculture in general in India, particularly there are a lot of things we are doing in terms of making women-friendly machines where women can drive it. We can develop a lot of production practices, zero tillage, particularly in SIP. We are actually scaling up zero tillage potato with straw mulching, which actually eliminates your plowing, all the land preparation there, digging, all these things which is mostly dominated by labor. We are eliminating those, so it's becoming a women-friendly production system for potato there. Similarly, any other crops, we are developing new systems which are much more women-friendly. We are developing small machines which can be driven by the women there. So the production system in general is moving towards that. The private sector will respond. If there are enough women there out there, there's enough demand, the private sector will respond to that. Developing the systems which is much more women-friendly there. But I think one of the things which is lacking from the government system is the land leasing. Right now, I think if you look at the last thing I read is the Land Leasing Act of 2016, which was drafted by Niti Aayog. I think it's still under consideration, and PM office has set up a committee. And I think that Land Leasing Act will recognize the tenant farmers as in the system. Right now, many landless laborers, particularly the women laborers there, who are doing farming on the lease basis, they are not recognized in the system. This particular act, if it is approved or passed in the cabinet, I don't know the process exactly, it will recognize those people in the system. So they will be, they will be eligible, they will be recognized in the institutional credit, pension, or any sort of government schemes, the government trainings, so they will be in the system if this Land Leasing Act of 2016, which is drafted by Niti Aayog. But again, the state has to implement it. It's a state subject. Eventually, the state has to implement that Land Leasing Act there to recognize this women landless laborer there. I'll give an example. In Odisha, I was working, when I was at IRI, I was working with 35 landless laborers who have leased land. Okay, I'm wrapping up. 1 minute. Landless laborers there, but they are tenant farmers there. They are there because if we want to introduce something, they have to get permission from the landowner there. They really cannot take up anything on their own there because they are not recognized in the system. They have no say in that. So I think the key is that Land Leasing Act will be the one key in terms of accelerating the gender equality in rice farming there.
Thank you. Thank you very much, Dr. Manti. Thank you very much. So friends, we come to the end of both the rounds from our panelists. Now it is an open round and we shall take questions and also comments required. First from the floor and then from the panelist. And we shall start in a reverse order. No, please listen. So if you have got any question or comment for Dr. Mohanty, specifically to Dr. Mohanty on two issues, gender and possibility of precision farming. So if you have got any specific question for Dr. Mohanty, you please put your question. You please raise your hand. The mic will be given to you and then you can put your question. Anybody from the audience? Yes, madam. Dr. Lipi Das.
Hello. Thank you very much. So good afternoon to all of you. So it's for Dr. Mohanty. Really, because you have focused on two particular aspects on precision farming and gender. So I'll just, because the jury, the sir has asked about the gender equality in rice-based production system. So actually, you can see that last decade, if you'll see the trend, the number of laborers is continuously increasing in comparison as compared to that is cultivator. So because an equality, if you are going to say the equality, first we have to identify focus on the equity first. Then only we can dream of the equality. And moreover, because the impact of male migration, and impact of male migration has certainly an impact on the women sectors. And women that is because we can see the de facto heads, because de facto heads can take the decisions. And so what are the points or what are the major that is strategic we can take up to convert, because we have to see the transition of a farm woman to women farmer. That is our motto, because you see in rural sector, we are not going to get that is recognized the women as a, that is that, yes, sir. That is what is the strategic points or plan that how could we see convert or transit a farm women to a women farmers so that they can direct the gender equity and ultimately the equality. Okay, thank you very much.
Thank you very much. Any other question to Dr. Mohanty? Yes, sir. Please give the mic. One.
So the previous whatever discussion Dr. Mohanty has informed concerning to farmers and the technologists. I am from CSIR CFTRI Mysore. Whatever we develop technology in the lab, we try to carry out the work in the field. When we go to field, the farmers will hesitate to accept our technology. So the best thing what our director and we made arrangement that we purchased whatever material what they have to dispose after harvesting, and that material be taken by us in front of them, and we carry out the work with them, whatever demo we have developed the technology. By that, the farmers will get the full confidence. We had done like that in one of Shivamogga district where high moisture paddy, how it was dried. We purchased 3 tons of paddy and we demonstrated our technology to them. They were so much happy. Even today, after 40 years, people are following the technology.
Okay, sir. Thank you very much.
So the best thing is that is the way to go for farming, helping the farmers.
Thank you.
That's one.
Yeah. My request is if you can put your question in only 1 or 2 sentences so that we will be able to cover large number of queries. Any other? Yes, Dr. Ponda.
Myself, B.V. Ponda, Principal Scientist from NRI. Sir, as far as gender equality in agriculture is concerned, I think our eastern part of the country, northeastern part, is still the land holding with women. And many of the states having that land holding with the men. And this management, as far as concerned, it's a family issue, many cases both involved. But whether there is any indication on any research, we can say finding that when the management changes from men to women, there is profitability or there is increase in productivity? That's my query.
Okay, Dr. Panda, thank you very much. Any of your panelists would have any question for Dr. Mohanty? No, good. Dr. Mohanty, you have got 30 seconds to respond all these three questions.
Yes, I think I'll start from the last one. Last one. There is evidence, there is literature which says that the management by women better than the men. There's a lot of literature you can look. And I have actually done research in Odisha. These two small SFLF, small farm or large field, one with the men, one with the women, and women in terms did much better than the man. Only in Odisha alone. I can send you the paper there. As Dr. Lipidas, I definitely the gender equality should start from gender equity there. I think I don't disagree with the fact that that it has to start from gender equity there.
Okay, thank you very much. Thank you, Dr. Mohanty. Let me share two very recent experience of mine. Just I think last week I was in the convocation of OUAT. Dr. Naik, you were also there. I think some of you were also there. Rest of you were also there. The students who got degree, around 60% plus were girl students. But this is not important. The students who got medals, 95% plus were girl students. So, and then after that, I went to another university, which is in Ranchi, Jharkhand, Visagri University. And they are, of course, not 95 or 65 plus, but then more than 50% students were girl students who got their BSc, MSc, and PhD degrees. So there is positive sign happening in the education sector. And of course, Dr. Agrawal just, I think, yesterday only he gave me some data. Yes, that currently on an average in the country, 46% of our students, UG, PG, PhD putting together, 46% are girls. And then in last around 7-8 years, the increase has been 25%. So 25% increase in very recently. So these are all positive development. But then at the end, I have got a complaint against Dr. Nayak or Dr. Agrawal and whosoever the complainant could be, you can register it. There should have been somebody from other gender also here in the panel discussion. Okay, but suddenly next time we are going to correct it. Good. Let's come back to the discussion now to Dr. Virender. And Dr. Virender talked about two issues, So if any specific comment or query for Dr. Virender Kumar. Anybody from the floor? Sir, Dr. B.N. Singh.
Thank you, Mr. Chairman. Actually, I have been working since last 10 years on the direct seeded rice. I call it aerobic rice because we irrigate it, not it's a run fed. I published a book also, and tomorrow I will be giving a seminar. We have to closely work with the farmers because farmers, they take the best technology available from different research institutes. What we are doing now, that we promote the technology which is developed by an institution that they do not accept. If some variety is available from Punjab, they grow it in their field, which is better than what we are recommending. So we have to closely work with the farmers. And then I found out that even the weedicide is not a problem. They apply the pre-emergence weedicide. Once we tell them that this is the way we have to do it, and they 100% there is application. And we got the result like even this year I evaluated the lines from Punjab for direct seeded rice. Yeah. And they are doing well both under the direct seeded and transplanted. So we have to see what are the technologies available. Tomorrow I will be talking on this in the morning session. And then regarding the Dr. Pradhan's, although this is not a comment, but some of the mega varieties like Swarna, Sambha Masuri, Pusa Basmati 1121, IR 36, IR 64. They were all developed by conventional breeding method. No marker assisted breeding. So we have to, as a plant breeder, we have to see what is the parent combination which will yield a recombinant after 5 years or 10 years of release. Already there are the variety which are having all those gene complexes.
Okay, sir, I think we have to be quick so that we will be able to take some more questions. Yeah. Friends, Dr. B.N. Singh is one of our very renowned rice scientists of the country. And also he is the former director of this particular institute. So, sir, thank you very much for kindly joining in this particular. Thank you very much. Dr. Nimai Mandal, quickly. Just question, 1 or 2 sentences.
Yes, sir. I have a query regarding the sustainability of DSR for Dr. Birender actually, because the fields which are continuously under DSR, there is a problem of the nutritional disorder around this thing. And recently, ED has also reported this iron deficiency in continuous DSR field. So how do you manage those problems?
Thank you. Thank you, Dr. Misra from the front row.
Virtually, I am concerned about the promotion of the maize instead of the rice, particularly in the Haryana, Punjab, and the central part of the Uttar Pradesh. Because if you know the situation, these areas are very much prone to the salinity and sodicity. And you know the rice is the one of the very, very important ameliorative crops. Then what will be happen on long-term basis? Suppose if you are growing the maize, particularly instead of the rice in these areas.
Let's have 2 sentences. Thank you. Thank you very much. Okay, so Dr. Birender, no, you have already asked so many questions before that. So Dr. Birender, over to you, 30 seconds.
Okay, I think first was comment, not a question. So we also work with the farmers. Most of the program is with farmers. So that's straightforward. Second, sustainability. I think, yes, for any technology, there's always trade-off. You have to look at what you're solving for, what are the major drivers right now. So if we have plenty of water, labor, I think transplanting is there, but the drivers are forcing us. And we have to address those sustainability issues by agronomic and the breeding solutions. Third one was about diversification maize. I also mentioned that we had to look at which option will fit where. And I also raised my comment that these areas are reclaimed soil. So secondary salinization could be an issue. So we have to look at which option will fit where, not the blanket maize everywhere. So we have to find solution. Thank you.
Good. Dr. Agrawal, your quick question. Yes. So Dr. Birender.
Of course, my question, if you see Punjab analysis, it talks rice, wheat, and maize, these 3 crops. It is audible, no?
Let's have 2 sentences.
The question, sir, I'll put 1 question, but 4 background sentences. Otherwise, the question won't be having any base. Punjab analysis by Planning Commission or Niti Aayog or other people have seen strength of the technology, one of the critical factor for tackling crop. That is rice, wheat, maize also equally strong technological viable crop. Second is related to niche of the crop. Maize was more natural than rice in Punjab. Second.
Okay, that's some, yeah.
Now my question, I'll put now question, sir.
Okay.
And MSP is there for rice also, maize also. With this condition, how much diversification plan for Punjab and why should not be possible when there is MSP and there is niche for the crop? That is my question.
Virender.
I think MSP is there, but it's not that MSP as we get in rice and wheat. Procurement, guaranteed procurement, that's give assured price. Maize, there's a MSP, I think there's a price will fluctuate. So that's the issue.
MSP is there, but then who is purchasing with that MSP?
Exactly,
That is the
still
question.
open market. A lot of difference between rice, wheat, and maize.
Good.
Yeah,
Okay,
thanks.
thank you very much. Now let's go to Dr. Nayak. Again, very specifically, if you have got any pointed question for Dr. Nayak. Yes, Dr. Panda. No, that you have to ask in the 3rd Indian Science, the Indian Rice Congress. Any question for Dr. Nayak? Yes, please.
Sir, good afternoon, sir. I am Dr. Srinivas from Andhra Pradesh, Anguru, representing Anguru. So regarding natural farming practices, nowadays most of the farmers are tenant farmers. In Andhra Pradesh, if you take around 80 to 85% are tenant farmers. So if you go on doing for this natural farming practice, what will be the future for that tenant farmers that we have to look after?
Okay, thank you. Thank you very much. Any other pointed question for Dr. Nayak? Yes, please.
A question to Dr. Ali, I think.
Okay.
Can
No,
I ask?
we shall come back there. Okay. Yeah. Okay. Any question for Dr. Nayak?
Can I cast that question?
Which one?
Can I I'm Dr. Ali. Yeah.
Dr. Johar Ali, please, please.
Yeah, since Nayak raised this carbon footprint issue, actually, I was trying to, this is a comment, more of a comment. The direct seeded rice hybrids offer a very good solution for low carbon footprint based on its high yield and shorter duration, and the less water requirement of the hybrids in comparison to inbreds can be a very good solution and reduce a lot of these things. And if you put them in puddle condition or intermittent irrigation thing, that can help a lot to reduce the carbon footprint. Yeah, that's it.
Okay, okay, Dr. Johar Ali. So, Dr. Nayak, any quick response to this? Yeah.
It was a comment rather.
Yeah.
So a lot of technology are available, that can be one of the technology, and it has to be tested.
Yeah.
With respect to natural farming, wherever the farmers are doing without applying any chemical fertilizer, if at all they are incurring some kind of losses, there should be some mechanism of a payment through ecosystem service that is doing, which we are not estimating. Only provisioning service they are getting. They are doing a lot of other services which society is getting, but the farmer is not getting. So those kind of system has to put in place where we are going for pushing the natural farming. Thank you.
Good. Thank you. Thank you very much. Now we shall go for the questions for Dr. Johar Ali. Any pointed question? Sir, you wanted to ask one question to Dr. Johar Ali? Yes.
So concerning to hybrid varieties, he said that head rice yield is less, he's telling. So there is already technology known that hybrid varieties, whichever variety is having lot of fissures inside the grain. If you go for parboiling, you get almost 98% head rice you're going to get. By parboiling, you are going to have nutrition will improve and head rice will also improve. Economy will also improve. There's so many plus points by going to parboiling, the different methods of parboiling. That is my suggestion to Dr. Ali.
Thank you very much. I think one more question from the third row.
Yeah, thank you. So myself, Dr. Sudhanshu, I represent Bayer Crop Science. I have a question to Dr. Johar Ali. He talked about the direct seeded rice and its impact. So why don't we have the end-to-end policy document, especially in states like Odisha, where government can promote hybrid rice, especially in the context of your carbon farming? We understand the impact of carbon farming and smallholder farming. At the same time, we get a lot of benefits of water savings and all these things. So why don't we have an end-to-end policy document to promote this?
Thank you. Thank you very much. Sir, your question? Yes.
Yeah, this is NP Singh from DCM Sri Ram. Dr. Johar Ali, actually, we know that the three-line system, hybrids now it is almost getting 4 million hectares area covering. And in between now we are going to introduce the two-line hybrid. Still there is a lot of scope to popularize three-line hybrid. And in irrigated conditions and in early maturity, number of hybrids are there. So putting one system and jumping into the other system, how it is going to work and how the hybrid technology we are going to say that yes, this is a profitable.
Thank you. Thank you very much. Yes, Dr. Pradhan.
Dr. Ali, you told about heterotic blocks, but till date we don't know about the markers, anything about the heterotic blocks. How you will be going with genomic assisted breeding for improvement of super hybrid? You told the roadmap about many policies. We have a problem of 200 gram like that. But if we will be providing the parental lines, we can increase the seed and we can test that. That will not be the issue. Main issue is that whether genomic assisted breeding through that, you have heterotic block, hotspot, you are able to have a genomic assisted breeding hybrid. That is my question.
Okay, thank you, Dr. Pradhan. Dr. Birender.
Yeah, I have 2 quick questions to Dr. Johar. Dr. Johar, what are your views about the scope of apomix trait in public bred hybrids?
Right.
And my second question is, how far we have progressed with regard to two-line breeding system in terms of identifying the right TGMS or EGMS lines? Or is there any further scope for improvement for engineered male sterility, either through transgenesis or through genome-editing?
Okay, Dr. Sundaram, Dr. Virender.
I have one question for Dr. Johari. I think for hybrid, have we done some synthesis about learning where it has adopted and why farmers adopted there? And in some areas where we have tried and but not adopted, why it didn't get adopted? What learning we can do? For example, if Bihar, if you see, you'll find district where up to 90% adoption, you'll find district 0% adoption. So within a one state, you see so much diversity. Why it is happening? What are the drivers for the adoption of hybrid and what are the issues which are not been adopted? Can we learn from the landscape?
Okay,
Thank you.
Okay, Dr. Virender. So Dr. Johari, there are several questions. It's really limited. So maybe
Okay.
And it is really
Yeah.
2 minutes. Yes.
Yeah, the first question was on the parboiling. Of course, that is, it improves the head rice recovery. But what I mentioned was generally the hybrids have a tendency to have 45 to 55% range. What we have brought out now is above 60% hybrids, 60% head rice recovery and milling recovery of 70%. The second is Odisha, why the hybrid rice, low carbon footprint, why do not we have a document on that or something from end to end? I think there could be a very good document prepared from end to end, especially for low carbon footprint on direct seeded rice hybrids, which would be a very effective to deploy and demonstrate the power of the hybrids in comparison to inbreds, and the people and the especially the farmers and the policymakers can very well view that as a good sign to upscale this kind of a technology. So I think that's a good suggestion. The third one is because I was trying to take a lot of things, but I'm the.
Okay, Dr. Johari, what we shall do is you can skip 1 or 2, maybe later you can answer.
Okay.
So what I have noted it down.
Yeah. Yeah, I will go to Dr. Pradhan straight because that was interesting for everyone. I think the heterotic pools, I mentioned heterotic pools, not heterotic blocks in particular. Heterotic pools are basically on the genetic diversity. You lay out all the materials and see which pools are very distinctive. And if you pull these pools, if you cross with each other, it will result in higher heterosis. And within the pools, you need to maintain them by intercrossing with each other. For example, B by B within a given heterotic pool and R by R in a different. So generally people mix these pools. As a result, when you mix these pools inadvertently, you are losing the heterosis and therefore you are destroying those pools. So in the future, what we need to do is we have to protect these pools, and very systematically we can do that. And with the genomics information now, when we are now.
Generally,
okay, that becomes too lengthy. Okay, I'll go to the next one to Dr. Sundaram.
What you can do is you can send their response to the respective persons you know, and we shall get back to you.
Okay.
Let us quickly go to the next one.
Sure.
Any pointed question to Dr. Sundaram from the floor? Yes, Dr. Mandal.
Thank you, sir. Sir, it's good that ICAR is investing a lot on this laboratory facility on this thing. But I want to know from Dr. Sundaram whether we also need to develop this phenotyping facility, particularly for the stress environment, for development of varieties for the stress environment.
Okay,
Thank you,
very
sir.
good. Next one. Yes.
Yeah.
Please go ahead. Please go ahead. Aap bataiye.
Yeah, Dr. Sundaram. As we know that some mega varieties, I will name them, that like MTU 1010 and Swarna, and in north, if you are going PR varieties. We know that whatever means QTLs or markers are available for enhancing the grain yield. Can we think of, can we put any project to take these mega varieties and give that 5% or 10% yield increase over that? Number one. Number two, by gene editing systems, is there any possibility to think of taking these varieties to make that yield enhancement up to whatever expectation levels are there.
Okay, thank you. Mridul.
Sir, I have just two concerns. One is that for genome editing targets, practically we know, means while discussing with all the scientists talking engineering, the main limiting factor is going to be the number of genes available to do editing. But till now, there is no number of genes available to do major impact. Even GN1 finally in the field, how much it will perform, it will be. Sir, another, my ICR at a policy level, sir, if you see in Japan, rice breeding, gene now need for discovering new genes and more genes for different traits. Now in Japan, when they do any breeding, mapping and other program, finally the Neil is developed in the Koshi-Hikari background. And that's why they have a very good advantage that whatever new genes they discover and their interaction, they can study in the same background. Yeah. But in India, so you have mapped some gene and Dr. Kuldeep Singh has mapped some gene. We got very good for BPH. Now, when we want to utilize this gene and their combination, everything is developed in a different background. Okay. That's why as a policy level, there is now need to, as genome editing needs genes, and to do that at policy level, now it should be in a single background, not whenever we discover any new genes or mapping, that should be in a single background so that their interaction can be rapidly studied and then utilized in our system.
Good. So Dr. Sundaram, quick response.
Shall I try to answer the query what you raised earlier, sir? Sir, as regards to why the initial efforts in biofortification, they're not given the necessary impact is that in India, say a very committed program in biofortification started with funding from DBT in 2008. When the program was started, the problem was that, there was no clear idea about genetics of the trait. We didn't have good donor lines, and the availability of genes or QTL information was also very limited. So that forced us to go for empirical breeding. And there were also controversies regarding the protocols for assessing iron and zinc. So this was the limitation. And now that the genetics is very clear, a few major genes are, now it is possible.
Okay.
And sir, the query raised by Dr. Mandal, I agree with you that along with gene editing for various traits, it is important to develop the screening facilities also. There is no argument in that. Coming to the question, sir, what you raised regarding mega varieties, biofortification is a very good idea. But the problem with biofortification is that here you're not working with major genes. We are working with QTLs. How easy it will be to reconstitute the mega varieties. Of course, we can use genomics-assisted breeding to reconstitute them by transferring multiple QTLs, which have got major or submajor effect. That's a question. And we are also working on that. And your question regarding yield improvement through genome editing, we have already demonstrated, not only our group, NRRI and IRA have demonstrated in different varieties like Sambama Suri, Swarna, and also in MTU 1010. And clearly, some of these mega varieties can be improved for their yield. Now, coming to last question of Mridul, I agree with you that it will always be good to work in a common background or develop NILs in the background of a particular variety. But in case of genome editing, the requirement of Punjab will be different from the requirement of Odisha or Tamil Nadu. And as the adage goes, one man's food is another man's poison. So we need to give a choice of products to the farmers, which they can use it.
Okay.
Let's discuss later.
That discussion will be later, Mridul. Okay. So, no, there will be questions for you now. Yeah. Okay, Dr. Sundaram. So thank you very much. Any quick question for Dr. Agrawal? Any pointed question? Any question from the panelist? Okay. This side? Yes, sir.
This is a question for both Dr. Agrawal and Dr. Pradhan. That one observation is that the rice yield potential, it can be improved up to 15.9 tons, according to the theoretical calculation done by Dr. Yoshida since last 40 years. That he has taken into consideration the energy value, then the field area, then the length of the duration of the plant, everything. So our technology has not gone beyond 10 tons per hectare. So this is one observation. The second one is that there are so many efforts to change the panicle architecture in relation to improvement of the grain yield. But they're not all sustainable, because when you look at the evolution of rice, the panicle changed from a triangular shape into the cylindrical pattern. And this cylindrical pattern has not been sustainable in our newly developed varieties. So this factor has not been taken into consideration. That's why when we increase the panicle size, a large number of grains are produced, spikelets are produced, but they interact among themselves, produce a lot of ethylene, and this ethylene is degenerating the spikelets. That's why the objective of increasing the yield potential is not effective. So this is my observation. Thank you.
Thank you very much, sir. Thank you very much. Dr. Agrawal, any quick response to that?
Yeah, thank you for such a big topic to be discussed. It is correct that you can have 20 tons or whatever biological yield from a rice crop per hectare. And with all our knowledge and possible plant type, 60% harvesting is 60%, 60.6 can be very viable. So if that logic, it is 12 ton, but a lot of technological breakthrough, understanding physiology better, developmental biology better, genome editing, it is possible. Like one example Dr. Pradhan was giving, and we know a lot of other examples in other laboratory in India or elsewhere. So it is possible to have, you can have ethylene production reduce, you can have more. Now zinc source we're talking, zinc source plus translocation is also a very important factor. It is possible to go beyond 15 ton. I mean, that is.
So finally, we come to our first panelist, Dr. Pradhan. Any pointed question? Yes. That's all.
Sir, I have, you put the first question regarding the platooning of rice production. He mentioned about the irrigated, but I'll just supplement about the dry land and non-irrigated rain-fed agriculture. He told that will take 2 decades. So I have some solution. We can bring it to 1 decade. Number one, in the Odisha.
So the point is, we have got very limited time. So,
sir, I request you just to supplement a very vital point. Okay. So 1 minute time, please. So Odisha, we are getting a 1500 millimeter rainfall. We are unable to manage it. For managing the irrigation sector, since inception, Odisha is irrigation department is there, getting 5,000, 6,000 crores and employing more than 3,000, 3,000 engineers. Looking after that, 35% land. We have 65% land is on the rain-fed. So it is high time this Congress must recommend to the government that we can employ, particularly the agricultural engineers are very trained in this maintaining the
next one.
Next one is particularly we can also second point. Nowadays government, both central and state government is issuing the rice, giving 1 rupee free rice, whatever it is. So that making a really complicacy in the rural side. I am also coming from rural side. Nobody is working in the field because now laborers is a problem. So they are just eating that free rice and also getting some money. And that is the reason actually the rice production.
Next one, sir.
Yes. So let the Congress to give a concrete suggestion. So thank you.
Oh, thank you very much. Yes, Dr. Rahul.
Sir, thank you, sir. I'll be very brief, sir. Sir, India has very low input use compared to other countries, particularly fertilizer. And as you said, we have not achieved the yield plateau also. So my question is, why we are shifting our focus from high input use agriculture to low input use? So is it because India has achieved the food sufficiency and we do not have the much storage capacity and we want to reduce the production of India? Or whether it is established fact that high input use causes cancer and other diseases, so we want to reduce those diseases? Or except cutting cost, what is the other motivation to shift to?
Okay, Rahul, thank you very much. Any other? Yes, sir.
This is a question to Dr. Sundaram. Dr. Sundaram, sir, my clarification is when once you produce a biofortified rice, any experiment or any work has been done after cooking that biofortified rice, how sensory-wise, texture-wise, taste-wise, how it appears, any work has been done in that direction, please?
Come back to Sundaram, just wait. Let Dr. Pradhan respond first. Any pointed question to Dr. Pradhan? Anybody from the panelist? No, Dr. Pradhan, your response.
Yeah. Dr. B.N. Singh earlier just asked one question, like very important mega varieties like Swarna and other, those are actually examples should be a set of process are successful. Sir, I agree to you. I started, that's why classical breeding resulted into success. We achieved green revolution and etc. food sufficiency. But thing is that we want many character, many traits, many genes to be pyramided together, maybe 200, 300. So how to use that? 2 to 3 genes, population size will increase. 200, you imagine. So that is the reason for making climate resilient, yeah, climate smart. We want all the traits together in a mega variety. Already mega is a successful one. Next, we want to make a smart version of the mega variety. So it's need like a genomic assisted breeding. That was my point. Second is about question of Dr. Samant Rai. So I told 2 decades why, genomic assisted just rice, a single publication has not come. So you can imagine in case of lowland rice, the variability, how much, where we are achieving again plateau in case of rain-fed rice, it will take definitely more than 2 decades, I am telling. Genomic assisted will start for irrigated ecology. Then we'll go to upland, then we'll go lowland. Like that, it will take a lot of time. That was my point of telling. Then question of Rahul is input use efficiency. Input use efficiency, we are using a lot of fertilizer like nitrogen, 40% only we are able to use. If input use efficiency like genes are identified and put in the genomic assisted in the training population, definitely we are going to save a lot of saving to the farmers as well as to the country. So about your other question, I don't know. This cancer causing, yeah, so much of those things are different aspect. So I think I covered.
Yes, Dr.
three.
Thank you very much. Thank you very much. Friends, let me apologize for that. I'm really sorry that I had to rush for many things. Number one, we have to conclude this. Another session is waiting, and also I have to leave. But then it has been a fantastic session. We really could entertain several questions. I know there could be several other questions also, and you will be here today, tomorrow, and day after also, so you can continue your discussion in the subsequent sessions also. Before we conclude, I shall request our co-chair, Dr. Agrawal, to please give your observation, and then we should go for the conclusion.
Thank you. Thank you, sir. And I shall be also brief. I know the time constraint is there, but it was a very enriching discussion. I think the way it has been structured, the way the responses have come, the audience participation, everything. So I thank all online and offline panelists, and especially our Secretary and DG Aisha, who has chaired this. He has a long experience in this. So a lot of these technical points have already discussed. During my recent visit to ERI, I think that time you were not there. I visited about a month back. And I could see the kind of research they are doing now, like how to reduce the cooking time of the rice. So you see, even if you make it half, so how much energy we are going to save? Okay. And that nobody is accounting for. Only we just say that we are accounting only for the food security, but energy saving also, and even this the emissions and other things, many kind of things really we are doing. And for natural farming, as the Secretary has told, we are also going to start now the UG and PG programs, and where, as it was suggested, that it has to be open program. So we are trying to make it open program and evolving program. We have to collect a lot of data for that, and then only I think we can really come out with this, because it's a national priority for the government. And I think for the gender balance also, we are moving towards the gender balance. In the selections, in the even in the students, you can see these are only the few figures which he has given. Even in Tamil Nadu, we could find 80% are the girls students, and they demand more and more hostels for the, because girls we cannot stay. We cannot ask that okay, you stay in the paying guest, or you stay outside. So at least those much we really we want
but we are supporting from ICAR everything. So gender balance in education also is going to happen. And in rice, I think already our experts have spoken. So thank you, sir. I'll not take much time. And it was really excellent. And all these points are, I think, the best recommendations which can go for the government for the adoption. Thank you, sir.
Just my last suggestion for you, all these questions were excellent, as I said. So at the end of this meeting, if you can just give us maybe for every question, 1 paragraph answer. So if all the panelists can give one, and that will be because these are the questions which are generally asked to anybody who is working on rice. And I am asked this kind of question on several occasions. So this will serve me particularly and also all of you as a ready-made kind of response from council side, from rice researcher side. So this is number one suggestion. And number two, this kind of panel discussion, I think it is very efficient, very, very efficient in terms of time, in terms of knowledge sharing, in terms of interaction. So probably in our future programs also, whosoever is going to organize, let us have this kind of discussion more and more instead of having one lecture for a longer time or something like that. See, within 2 hours, we could listen lots of things. Of course, plenary lectures will be there. Those have got some other importance. Those are very, very good. But then whenever time permits, let us try to have these kinds of panel discussions so that we will be able to accommodate a large number of panelists and also a good number of questions from the front. So I congratulate the organizers for thinking about this and also organizing it so successfully. And of course, asking me and Dr. Agrawal to co-chair the session. So thank you very much, all of you. Thank you.
Thank you very much. You know what? Yes, sir. Yes, sir. Yes, sir. Thank you. Oh, so what a discussion. You know, as usual, Indian Rice Congress is setting a strong legacy. So, you know, our hearts say, let it be continued. But our minds say every good thing comes to an end. To be on schedule, we need to be on time. So I now request the chair and co-chair, sir, please felicitate our panelists with a small bouquet, not bouquet, mementos. This is to show our gratitude and respect and for your time for this Congress. Thank you. We have 30 seconds left to conclude this session. So now our convener from the organizing side is requested to felicitate the chair and co-chair. Sir, 30 seconds, please. We need 30 seconds more. I'm requesting convener Dr. Sanjay Shah to felicitate. And then to the co-chair, Dr. R.C. Agarwal. Thank you very much. So we had a formal vote of thanks, but due to time limitation,
आएंगे,
Okay.
announce कर दूं और
Okay.
अभी तुरंत नहीं।
So now you are going forward to the next session. The evening talk by Dr. T. Mohapatra, former DG of ICAR. And he is now arriving, so I request all the participants to be seated.
After the tea break, we'll be starting the evening talk by Dr. T. Mahapatra. So please assemble in the hall as soon as possible. Huh? पूरा पूरा उधर तो चेयर रहेगा, दो टेबल नहीं अरे यहाँ रहेंगे ना, इसलिए इसको हटा देते वहाँ रखिए हाँ एक्चुअली यहाँ तो क्या होगा ना, ऐसे करके देखेंगे पीछे बैठेंगे, इसका वहाँ कर देते जो भी बोले अगर आएंगे तो इसके बाद हो गया खत्म, उसके बाद एक क्वालिफिकेशन मिलेगा, उसके बाद ये दोनों खत्म
ये सब बंद करेंगे ना, इसकी जरूरत नहीं है ना सर, इसकी जरूरत नहीं है ना।
Hello, 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 hello. Hello, 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 hello.
संतोष जी NRI लेक्चर करके लिखा हुआ है। संतोष जी मिला? I request the delegates who are sitting on the last rows, they can come forward. Please come forward. We are about to begin the evening talk. आवाज नहीं आ रही है संतोष जी? Hello. Hello. On तो है. हेलो संतोष जी ये एसी का टेम्परेचर थोड़ा बढ़ सकता है क्या? आवाज नहीं आ रही है, थोड़ा एसी का टेम्परेचर बढ़ा दीजिए। हेलो, हाँ इसमें आ रही है। एसी का टेम्परेचर थोड़ा बढ़ा दीजिए संतोष जी। हाँ बहुत ज्यादा ठंडा हो गया है। नहीं नहीं सर, so our guest has arrived for the evening talk today. So I request all those who are standing in the lobby, they may come and take their seats so that they can start today's program.
हेलो हेलो।
कौन सा वाला है?
हेलो हेलो। हेलो 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 हेलो।
Good evening, delegates, ladies and gentlemen. Welcome to this evening academic treat. It's my pleasure and privilege to announce that we have with us one of the most renowned researcher, academician, teacher, a great motivator, and above all, a motivation himself for researchers across disciplines. Ladies and gentlemen, please welcome Honorable Dr. T. Mahapatra, ex-Secretary DARE and DG ICR, who is going to deliver the most awaited evening talk today on transforming rice research recent. Yeah, on nurturing rice for bountiful harvest, new paradigms for sustainable food security. I request Honorable Director NRI to welcome the guest with a bouquet of flowers. Thank you, sir. As I said, the speaker of today's talk is not only known to audience of this auditorium, but to whole agricultural fraternity across the world. But as a custom, I would once again request Honorable Director NRI, Dr. A.K. Naik, to please introduce the speaker to the audience. Director Dr. A.K. Naik, please.
Good evening, everybody. I think Dr. T. Mahapatra does not need any introduction to this audience. He is one of the internationally acclaimed scientists, guide, philosopher, mentor to all of the rice scientists, all of the NAS scientists. I think we are very much thankful that he is here to deliver the evening talk. So I think with this, I would like to invite Dr. Tilosan Mahapatra ji to deliver his evening talk. Thank you very much.
क्या वो तो है कॉलर माइक नहीं है ना नहीं है चलो कोई नहीं Good evening, everybody. Dr. Naik, Director of the Institute, and many dignitaries of the dais. Dr. B.N. Singh Saab, Namaskar. Nice to see you after many years. Professor Mahapatra also is also here, and many others. I should not take names. And delegates, it's a pleasure and privilege to be here. So I was contacted by Dr. Saha some months ago to come over here to deliver the lecture. So after some time, I reluctantly agreed that I have come several times here and given evening lectures, so extempo, and no new idea to talk about. And so while hesitating and finally agreeing to come, I had something in mind that rice is very core to my heart. Worked for almost 20 years. And still continuing, getting associated and then trying to understand rice. The complexities the crop offers is quite challenging. People say that so much research has been done in rice. Starting a career in rice is suicidal. Better you go to crops which are untouched, and little work there will bring you recognition. Partly true,
But rice offers challenges to innovate. And rice remains unexplored to a large extent. So I thought I'll speak on few points which are fast emerging, maybe 2-3 points. And earlier I mentioned those here in this auditorium. I'll elaborate on those bit and highlight why one has to build more research for tomorrow. So this topic I was asked what to really speak about. So this I have chosen very consciously. One, this is evening lecture, must be tired. For the whole day you have been busy listening to experts and also stalwarts, luminaries, Honorable President of India, Honorable Agriculture Minister and others. So I would like to be brief. So that's what I have chosen. So maybe they have given 1 hour, so I'll try to finish before that. So what is that I would like to say? My first part would be what we could do in rice. Is it fairly good, satisfying, where we stand, and what we really need? And what are those emerging ones, aspects and areas that need to be really focused on, particularly in the context of nurture. It's not just the literal meaning of nurture, which I'm going to talk about. And it has a genetic sense. So we'll see how best we can nurture rice, how best we can use new technology to nurture rice, to get best out of it, so that there is sustainable food production. And that's the bottom line, the sustainable food production and sustainable rice production. We are producing rice, but how do we continue producing at this pace, or even little at a higher pace, without compromising the sustainability part of it? There are several pillars of sustainability, and I believe there will be lectures on this. And how do we address at least some of those aspects of sustainability through these new science which is emerging, getting foothold very strongly. Indian agriculture has done where it works. Okay. Indian agriculture has worked fairly well. And this slide you will find, I have been presenting this for almost 6 years. And earlier, Dr. Mangla Rai actually started presenting this aspect. Just to highlight that how far we have gone over a period of time, and fairly long period of time. Now 70 years almost. So this is simple mathematics, arithmetics. What we produced in 1950-51 or in early 90s, different periods, baselines for different crops and commodities, and what we are actually producing today is quite satisfying. Satisfying because we are feeding 1.4 billion plus people. Satisfying because we are exporting. Satisfying because our exportable surplus far surpasses that of our needs. And consequently, say if you take the example of rice, we export. But in the process of this, we are also exporting water. We are also exporting in the form of cheap labor, whatever is available in the country. And we are compromising with the sustainability, the productive potential. And what extent we have compromised, I'm not going to really deal in detail, but during the course of seminar, probably we'll be discussing all this. So I'm not going to really tell you one by one how many times we have increased, but some examples you will see as we go along. And this is one example in recent history during past 5-6 years. We were hovering, our production in pulses was hovering around 15 to 16 or 17 million tons. And there comes a jump of 6 to 7 million tons, and now 8 million tons. And sustaining with that increase for 6 years, 7 years, continuously, despite problems, adversities. So what happened? Why this kind of revolution in production of pulses? Always we need to analyze to learn lessons. And we had the revolution, the Green Revolution, largely because of wheat. And Dr. B.N. Singh gave me those early articles and how Jaya and Padma were produced in addition to IR-8, what kind of crosses were made. So in fact, those papers I passed on to my colleagues here to keep record and how this institute contributed, and must take credit for this monumental work on the work on development of Jaya and Padma. So this particular phase is characterized by 4 important points. One, technology transfer and adoption, particularly in the form of new varieties. The breeder seed indent increased. The truthfully leveled seed production increased through seed hubs. So new varieties going to the field and variety replacement rate reaching to the extent of 80%, in pulses. And this is on record. So this is something which was unthinkable, and that happened. And that happened, that's the first point, and which pushed the production. Concomitantly, there is also area expansion happening due to 3 policy decisions of the government. One, that there will be a buffer stock of 2 million tons. 2, the MSP increased significantly. And 3, that there would be procurement happening, public procurement happening. Though limited, but public procurement happened for the sake of having the buffer stock limit fulfilled. So the policy decision pushed area expansion and also enabled technology reaching the farmers, and no new technology coming from outside as it happened during Green Revolution. So you have this production jump, and we are sustaining with that. Still, we are importing to the extent of 2.5 million tons. And if we can support this particular activity further, I believe in another 1 year time, it should be possible to have complete import substitution. It requires a bit of strong will and little push to what we have been doing. And it should not be difficult. But the fact is that a recent success story of Indian agriculture is exemplified by pulses and productivity and production increase in pulses. And similarly in sugar, today you must be reading about E20. E20 is ethanol 20% mixed with petrol. And many cities are already selling E20. And there are questions whether our vehicles would be able to run with a 20% mix of ethanol. Brazil runs with 40%, 40 to 50% ethanol mixed with petrol. And there is a scope to run vehicles with 80% ethanol. How this happened? And the success story, which is briefly highlighted here, is due to the disruptive technology, which is responsible for the recognition of Dr. Baksiram with Padma Shri, the coveted one this year. Let's give him a big hand. How science gets recognized. And this is a beautiful example that if one really does and contributes to that extent, one can certainly get such recognition. Maybe there is certain amount of delay, but it does happen. So what is the technology? It's a new variety reaching more than 90% of area, say in Uttar Pradesh, and providing 6 to 8 million tons of more sugar. And we don't require so much of sugar. So sugarcane juice getting diverted for bioethanol production and ethanol. Now we have almost reached 10% of substitution and 20% we are targeting, and we have started. It may not be 100% of the petrol mixed with 20%, 20 parts of ethanol, but it's already 10%. So this is a beautiful example of technology-driven development in energy sector, import substitution happening in non-agriculture sector due to agricultural technology. So this is unparalleled in history, and agriculture is so highly satisfying. And this happened during past 5-6 years. So 2 examples and where ICAR has led from the front, technology not only developed, but also taken to the field, implemented, and that's what I was mentioning in my foundation day lecture at IMTech Chandigarh, that how transformational changes can happen by using technologies. And this is a bright example of such technology. Where it is, doesn't happen. And we did analysis, Dr. O.P. Yadav, Dr. B.S. Dhillon, and myself. This was published in Current Science. Often we paint a very pessimistic picture of what is really happening. And this is with regard to the cereals, rice, wheat, maize, pearl millet, and sorghum. How we have really performed over a period of time. We always keep telling that we are dying, the whole thing, farmers are dying, and the whole country is suffering, everything is gone, and we are going to lose out. A pessimistic viewpoint, and that is often appreciated actually. It gets wider coverage in press and media. The Paddock brothers, the Malthus theory, all that got wide coverage, global level. And such coverages are always, they attract attention if it is negative. If it is positive, nobody notices actually. So how you analyze and how you interpret. So you can conveniently choose a particular portion of the data and then say that it's negative. And that's what often is done. So when we did this analysis, taking the period starting from 1950 to 2017, and dividing that period into 17 years, before Green Revolution phase, and post-Green Revolution, and then recent phase, 4 phases. And then we discussed a lot about this, and then how to really choose the period, and what to really choose. So I'll highlight only the rice part of it, and you can read this paper, Current Science paper. It's not much highlighted. This is not to say that we should be complacent. Complacency should not be there, but we must not undermine the power of science, the efforts of scientists, and the efforts of the farmers in this country. Because our policy making also gets distorted because of the negative picture, highlighting our failures than our successes. This is a very, very important message. And I believe youngsters particularly would take note of this. And then we analyzed what is that gain in productivity in terms of kg per hectare per year, and how we have moved over a period of time, and whether we have failed or we have really done pretty well. And you can see the picture for rice. And this is there for these crops, and we say that there has been evergreen revolution in cereals. And you will see in that paper we have highlighted this. And see the way we have moved. 1967 to 1983 phase, that's the green. And prior to that, what was the kind of situation? And B reflects the kg per hectare per year, that gain we have over previous ones. And you can see what happened during Green Revolution phase, and what happened post-Green Revolution phase, and then what happened during 2001 to 2017. So we have not really fallen behind. Quite satisfying. And that is something quite creditable. And some important reasons and factors contributing to this, they are all given here. But they're not all. It's not a comprehensive list of factors which are influencing rice production. So similar such analysis was done for wheat and for maize and for pearl millet. In these 4 crops, rice, wheat, maize, and pearl millet, we have done exceedingly well. Of course, in case of sorghum, we have lagged behind. There are many reasons, I'll not go into that. But this is to say that fairly satisfying situation for us. And that is probably the reason why we are exporting close to 20 million tons. And we have such a huge buffer stock. We have given free ration for more than 80 crore people for more than a year. So that is something which that was unthinkable earlier, but today we could do this. So we are feeding comfortably 1.4, and today we are most populous nation and 1.4 billion plus people. So that complacency, as I said, must not be setting in, and we have challenges. We have enough at this point in time, but few years of drought, few years of famines, calamities in different formats, and we know this country is very prone, changing climate, so on and so forth. So obviously we can't be complacent. And we have sustainable development goals before us, 17 of them. And if you go to FAO site, FAO relates each one of them with agriculture, directly or indirectly. And it has explanation why a particular sustainable development goal and how it is linked to agriculture. So agriculture finds mention for each one of them. Even sustainable cities require sustainable food production, vegetable production, fruit production. The life underwater is linked to agriculture, aquaculture, and various other things. I'll not go into those details, but that itself would require a big lecture. And rice, some people say, some authors say that is consumed by almost 50% of population of the world, 8 billion people, and will be close to 10 billion by 2050. So it will be a huge population, even if 40% of people consume rice. So Dr. P. Samal is not attending. So he has given an estimate. It's a beautiful paper. I think other colleagues from NRI are involved in giving this estimate. Recently published, 458 million tons, or something like that. There are many different estimates. That's the global requirement. So huge requirement for no hunger. And no hunger is related to, zero hunger is related to no poverty. So no poverty, zero hunger, the first two. So zero hunger is linked to no poverty, or no poverty linked to zero hunger. And rice plays, agriculture overall plays the pivotal role, most crucial role, because we are still the rural India, rural population. Poverty is there, mostly the rural poverty. There's a very significant decline in poverty. If you see the multidimensional poverty rates and how it has declined, I'll not go into those details and bother you with the data, but it is very significantly declining. Of course, because of COVID, there is a break, but still we are moving very fast. And there is a significant role of agriculture and rice culture, rice agriculture in that. So how we can really meet these sustainable development goals and how best we can meet them. And that's the reason why the United Nations have been focusing on agriculture almost every year, some aspect of agriculture. And this year is the International Year of Millets. And you can see almost every year, barring few years in between, almost every year, whether it is soil sustainability, family farming, and International Year of Fruits and Vegetables, and so on and so forth. And 2004, we have an International Year of Rice. So on 25th year, when we celebrate rice, and that time the call was, the clarion call was, rice is life. Rice is life. Should we forget that slogan, that rice is life? What all we committed in 2004? Have we done all that? Are we moving to achieve the sustainable development goals? Actually, the whole world is lagging far behind. The recent analysis says, and because of COVID, because of war has led to displacement. Conflicts have been in the past and now also. COVID, conflict, climate change, the three C's, often highlighted at the global level, causing quite a bit of disruption. So this is what is very, very important, that we must revisit what all we committed. And it is time that the Second National Rice Congress should recommend and build a paper concept for another International Year on Rice. So another International Year on Rice. Maybe sustainable production system, or whatever you choose, that could be a sub-theme to highlight. Rice was life. Population is growing. Climate is changing. The natural resource base is degrading. So limitations are so many. How do we sustain? And rice ecology is threatened. The challenges are so many. So this is the time that when we become 25 years, celebrate 25 years of International Year of Rice to 2024, in 2029, we should have another International Year on rice. Not on rice, maybe sustainable rice production or whatever, sustainable rice intensification, whatever you write. So there should be a deliberation and a recommendation on this. Let India again lead. International Year of Millet, India led, and India is pioneering. During my tenure as DG, we did a lot of work on this. So this is the year, and it's going to be inaugurated shortly. So this is what I thought we should be doing, and a recommendation. Where is the change actually? How it changes? So what do we need actually? What do we need? And this is taken from the NRRI Vision Document 2050, which we prepared in 2013 when I was here. And this aspect, Dr. Naik was associated, the present director, and Dr. Samal and other colleagues. Dr. Saike is here. So they were involved in making these assessments. It is in vision document and it's already there in the website. So what do we need? And if you have the growth rate 1.56% or 0.3436%, which was there then at that point in time, and had we continued in 0.36% growth, what would have been our situation? If you see 2025, we are 2023. So 2025, if you compare where we are, if you see it doesn't come. So if you say 2025, population very much close to that actually is 1.42 billion. And it was estimated as 1.46 billion. Very close to that, what was estimated that time. And projected demand was 116 million. And we were growing at 0.36%, and 2025, 102 million tons. And actually we grew little faster. And we are how much? More than 120. And I am told 132 million tons or whatever. So whatever it is. And this year there will be some reduction. So these estimates would be finalized later. But we have reached there pretty early, 2 years before that, 120 million tons. And if we continue at this rate, it would not be difficult to reach the target by 2050. What was estimated that we need 137 million tons. And we would be very much there. We are already there, close to that, 25 years before. Science-led development, technology going to the field, area expansion hasn't happened in case of rice, mind you. So it's a technology-led growth. Productivity is increasing. We might in comparative terms be producing, our productivity might be lesser than other countries. There are many examples. And in fact, often we are blamed for this low productivity. But we should be careful. We should not blindly accept the arguments of others that we must increase our productivity and the different aspects of it. 290 districts of this country consuming 85% of fertilizer. And out of 700 odd districts, imagine 300 consuming 85% of the fertilizer. And 400 districts consuming only 15% of the fertilizer. There are many dimensions to what we talk about. Without going to the details of it, we often fumble because we don't have answers. Nobody questions. So there are issues, and similar is the situation with regard to pesticide use. So we would have been falling short of our expectation and requirements had we grown at that level of 0.36%. But as I said, we have not taken into account many things. We have not taken into account many things. And they are all indicated here very briefly. In this assessment, we have not taken into account how much we should export. 20, 30, 40. What is the global demand? Where is the global demand? Rice consumption in India is declining. From 85, we came down to 75. And we might come down to maybe 55 or 60. Not in distant future. kg per person per year, that's the consumption. So our consumption is declining. And that could be one of the reasons why there is more surplus. But population is growing. So total requirement would increase. But Africa is demanding more rice. Diversified needs of the consumers are to be met. The climate is going to dampen production. And that's a very, very important factor. And you know, your own study at this institute says that even the carbon dioxide increase would enable more productivity because of carbon dioxide capture happening more. But temperature rise concomitantly happening would be leading to upset of that advantage due to enhanced carbon dioxide concentration in the environment, atmosphere. So back to square one, that would be negative situation happening because of climate change. So if that happens, so obviously we have to account for that situation. So declining consumption domestically, enhanced consumption elsewhere globally, the climate change and diversified needs, and very importantly, the declining resource base, the degradation of natural resource base has to be accounted for while doing all this assessment. It cannot be just growth rate based, the population growth rate, the consumption pattern, and then how much we need. That's not really holistic assessment that we need. So we need to have that kind of reassessment done. But the bottom line is the sustainable rice production system, food production system, and how do we really do this? So I'm going slow, so I'll accelerate now the pace. The background is set. How do we nurture rice better for sustainable production or sustainable increase in production? How do we do this? What could be our parameters? So as a rice scientist, all of you know what are the components of sustainable production system. I will highlight 2 or 3 important points. I'll tell you what is actually nurture and how and what context my discussion would be actually centered. And then I'll highlight 2, 3 points how we can really address those. Nature versus nurture has been a long debate. It's a long debate. In fact, Shakespeare himself mentioned in his own novel, The Tempest, there are characters, and one character was described that his nature is such that nurture can never stick to that. That was the first time the nature, nurture words were used to describe that the trait, inherent trait of a person, and the nurture, the upbringing, cannot make any change in the nature of a person. That was the kind of viewpoint that was described in the novel, The Tempest. And subsequently, John Locke gave an alternative viewpoint that when we are born, it's a blank slate. And only subsequently, the innate ideas and the knowledge, they are developed and determined through our experiences as we keep encountering various situations in the environment. So slates start getting filled. And then it was largely because of nurture that we get from the environment. So quite divergent opinions, the nature versus nurture. And in fact, Francis Galton, a brilliant man, brilliant mind, he has done many things. And those who know genetics, studied genetics, they know contribution of Galton. And since there are people from various backgrounds, I'm trying to really simplify and not to go to the jargons. But he wanted to really give a clear-cut definition, differentiation between nature and nurture, and the relative importance of that. He took twins, monozygotic twins who are actually genetically identical, and tried to find out the impact of the environment. And he did find a predominant role of nature, but nurture did make a difference. The summary was that both are important, but nature being more powerful and important than nurture. That's what the twin studies reveal. And that's what is described in his book, Natural Inheritance, published long back, 1889, much before, just before Mendel's work. And that's what is highlighted here. The Canadian psychologist, Donald Hebb, he was asked a question more recently in 20th century. And that book was published in 2004. Question was, of nature and nurture, what contributes to the personality in human, being a psychologist? So he had detailed analysis. And he said that in a triangle, length matters or breadth matters or both matter to get the area. The way both are important, and similarly, both nature and nurture are important to get the personality. So that's the kind of nurture versus nature story. And we have come a long way, actually. Things don't move, actually. Okay. So this is the concept of heritability. There will be delegates who do not have background in genetics, that if you have the plant height 100 centimeter and you find, make a cross, and you find in the population the kind of individuals you get, you never get that kind of situation getting inherited. Expression not having 100%, maybe 50%, maybe 20%, maybe 90%, but hardly 100%. There could be situations where 100% expression happens in case of Mendelian traits, but most of the complex quantitative traits, as you see, majority of the traits of agricultural importance. So genes versus environment, and genes and environment and how they interplay. And then you can see in case of human that back pain was found to be heritable in different environments, in different genetic backgrounds when they were studied, to the extent of 21 to 67%. This is a recent one published in 2013. So what happens to the rest? Why we are not able to explain? Many of my colleagues who are doing GWAS, whole genome association studies, genome-wide association studies, you don't explain 100%. You have a loci explaining 5%, 10% of the total variance. And if you take 20 loci, 30 loci, you don't even go up to 70% of the variation. that you see for the trait. So that is much beyond the genes that we play around. So genes are not all. So there is something beyond genes. And that is controlled by the nurture component of it, the environment component of it. And we know very well, we talk about stability and Everett Russell's model, plant breeders know very well. And how the rank order of the varieties or strains change. And we say that they are stable or unstable genotypes. There are concepts of genetic plasticity, adaptability, the same genotype not behaving in different environments similarly. Same genotype, forget about twins, same genotype. In case of plants, you create pure lines. Doesn't behave similarly. Why? That component of nurture. Nurture is so important and powerful. In fact, there was a time when Lamarckian concept came and it was discarded. But today, we are revisiting the Lamarckian theory. The acquired characters getting inherited. There is another dimension to that. This complexity of nurture. So I'll not have time to explain everything. So it's already 6:34, it started a bit late. But you will not have patience to actually sit through if I go on explaining. The inheritance of acquired characters of Lamarck. So though we discarded that it talked about more frequent and sustained use of particular organ strengthens the organ. That's the first law. We had discarded it. And second said, all that nature has caused individuals to gain or lose by the influence of the circumstances is conserved through generation. Far more devastating at that point in time. It conserved through generation. You acquire it through use and disuse. And it goes through generations. So we believed more of Darwinian theory. There is genetic variation. Selection happens in the environment. The fittest survive. You select that. Nature selects that. And that survives. And that is how evolution happens. Nothing beyond that. They're all genetic. But there is something which is above genetics, beyond genetics, and that is called epigenetics. That is called epigenetics. And that is the core of nurture. Nurture is not just environment manipulation to get the best of it, but nurture is that a small part of that, some part, I'll not say small or big, some part of that change which happens because of a particular environmental situation also gets transmitted through generations, and a new trait is gained through epigenetics. No genetic change, but epigenetic change in human. You have to be careful what you eat. You have to be careful what you think. So Indian philosophy, that's why emphasizes on that. Your food matters. I'll not really talk about that. Some other day I'll have, only lecture on that. How food matters. How your thinking matters. How your emotions matter. how the affection of mother matters, how the mother's womb epigenetically controls your early developments. So how mother's thought and food matters, and how the epigenetic factors of plants what we eat, control genes in human. Control genes in human. Don't think that what we eat doesn't matter. What we eat, that matters. So that's some other day we'll have a lecture on that. More exciting. So nature and nurture, I have already said. So that is the organism we get. And this is a very good article and a very good book you must read. Don't go backward. So go forward. And so that we go fast. So nature versus nurture, or nature and nurture, or nature via nurture. So this is the most important point, that nature via nurture. How do we have a rise, productive rise, sustainably taken forward, that productive situation, maintain in different environmental niches, and providing food and environmental security? How do we enhance that nurture component? And how we have new science contributing to this nurture. So now, this is what is actually explained here. You have genes in the genome, G, and you have epigenome. I'll explain what is epigenome. And genome, ATGC, sequence same, but because of modification in the chromatin, the DNA, extraneous ones, so you have epigenome, and epigenome is responsible for which gene is going to be expressed and which is not to be expressed. What is going to be expressed in cell type 1, in liver cell, or in root cell, and what is that going to express in anther cell? That is the epigenetic component, the nurture component, and that is determined. And that is the more powerful part of it. And then that determines the transcriptome. So genome, the basic sequence is of course essential. Without that, it will not happen. Epigenome controls that, regulates that, and then comes your transcriptome. This transcriptome gives you protein, the proteome, the sum total of all proteins. Protein can control epigenome and can control the genome, and also controls the metabolome. And today, the new concept of lipidome, and the lipidome in disease resistance or cold tolerance in rice, for instance. There's a recent paper, you can read that. How lipidome, the lipid profile, the sum total lipid profile, and what are those lipid biomarkers which are responsible for cold tolerance, say, in case of rice or other crops. So all these, and finally giving you the phenome. When I formulated the phenomics project at IRI, and I never thought, I thought through imaging we'll understand the phenome. But phenome is so complex. Phenome doesn't happen because there are a set of genes. But you have all those, the epigenome, the transcriptome, the proteome, the metabolome, the lipidome, the ionome, and all that influenced by environment. All that influenced by environment. And that's the reason why the plant breeding remains partly art still. The plant breeding still remains art, partly. You develop a variety, you do not know which one is going to click. Every variety is not going to be Swarna. Every variety is not going to be Swarna sub 1. It might give you in 3-5 locations of your all India trial best result. When it goes to a state and grown in thousands of hectares, it falters. The adaptive mechanism is not there. That's the reason why I learned Dr. B.N. Singh when he was there. He focused on this. Mini kits, distribution, adaptive trials, large scale. You can release a variety, but it may not click. The epigenome adjustment has not happened. How best it is able to adjust in the growing environment, give you the best out of it. Whether you are able to provide that best environment. So that will determine the success, they determine the success of the genotype. The nurture part of it. It's not child's play. Breeders are often blamed. You have developed 30 varieties. How many have clicked? Maybe nothing clicked. But you should not stop. You should not stop. So continue working on variety development. Your genes should be there to start with. A genome should be enriched for genes of substance, for trait, and then a good environment for epigenome to express and produce the rest of the things. And finally, a phenome, the sum total of phenotype that we see in an organism, any organism. But layers of complexities are there. And this is where I have taken this example that what you feed to a fly, honeybee, determines whether it is going to be male or female, whether it is going to give you, it is going to be queen or going to be worker. They are born same genetic composition, same genetic composition. There are many examples. I have taken just one extreme example. So food will determine whether it's going to be queen. So give jelly, royal jelly, to a particular individual, and whosoever given royal jelly would become queen. And that will be developed ovary. It will provide, give progenitors and offsprings, large number of them. Keep providing large number of offsprings. And p-coumaric acid, if it is there, so it will give only workers. And that happens when royal jelly is not provided to the workers. Very good study. So the nurture influencing the nature, sex in this particular case, but there are plenty of other examples. So let me go fast. The epigenetics. So I have already explained that our cells and tissues differ. Genetically, they are same, but their genes expressing are different. They are determined at certain stage to give you a particular organ by way of a particular genes getting silenced, by way of particular set of genes allowed to express. A particular organ gets formed. So cellular differentiation happens through these epigenetic means. In different environment, stress situations, you have different genes expressing, different varieties expressing different genes. There are different layers of complexities again. And towards the end, I'll highlight one more complexity, which is different from the genome of the plant itself and how it is happening. And epigenetic patterns may change throughout lifespan. Genetic composition doesn't, except the red blood cells, which produces immunoglobulins, where the DNA rearrangement happens in the cell itself. And in that, different kinds of immunoglobulins are produced to attack different pathogens entering the body. So, except that, the other cells, the genetic composition remains same, except some somatic mutations which are accumulated. So epigenetic signatures influenced by the environment may determine appearance, may determine behavior, may determine stress response, may determine disease resistance, and even longevity. And I have given references. If you are interested, you can read that. So, friends, it's a very, very crucial aspect of it. I don't know, this doesn't work. सिस्टम को देखो भाई, काम नहीं कर रहा. हाँ है, क्या करना है? So I'll explain briefly, and I don't know whether you are able to read this, too much of information, but I'll explain you because it's very important. It's not a classroom teaching. This is a conference one, but I thought for the youngsters it will be useful. But this is a new concept, nowhere it is being taught about. So you have all kinds of environmental situations. You have drought, you have flooding, you have heat, you have salinity, you have pathogens, you have pests, all kinds of situations in the environment. And that leads to AP mutations. What are AP mutations? It's given in this oval structure. That DNA methylation, the CS3 group getting attached to, say, cytosine. There are sequences called CG islands, cytosine and guanosine together. It could be CHG islands. It could be CHH asymmetric islands. And C getting methylated. And methylation may happen by enzyme called methylase, or demethylation, removal of methyl group happens because of demethylase. There are genetic mechanisms, may be triggered by environment. That's very important. There could be changes in the histone, the chromatin. Acetylation of histone might alter gene expression. There could be RNA-mediated regulation because of small RNAs. 21 nucleotide, 22 nucleotide, 24 nucleotide, they're being formed. There are different the enzymes which are responsible, and they're going through the cycle of producing these methylation changes. And in the process, causing methylation, demethylation situations in the plants. So this is how your epigenetic changes happen, epigenetic mechanism in the oval structure, the three different types which are highlighted. And when epigenetic change happens, that is called a epimutation, in contrast to a mutation where nucleotide change happens. Here ATGC sequence is not changing. If you do sequencing, you'll get the same sequence. But if you do bisulfite sequencing, whole genome bisulfite sequencing, so WGBS, that's called WGBS, in contrast to whole genome sequence WGS. You will find the kind of methylation which has happened in the whole genome. And that whole genome methylation pattern is called epigenome. And study of epigenome is epigenomics. And the genetic effect of these epimutations constitute a new branch called epigenetics. So epigenetics and epigenomics is the area of new science, environmentally triggered, and a part of it inherited, transmitted, going to the progeny. You can select and create those adaptive epi alleles, and epi alleles contributing to trait improvement. And you can do selection. And that's what I want to highlight. And how can you serve rice better? Not just providing a better environment, but first of all, understanding and creating the epi alleles understanding the epigenome, understanding the epigenetics, and the genes thereof, which are undergoing changes, and in the process giving you a trait, we do not understand many traits because the studies are so meager globally. So what happens, just a minute, go back. So I have already explained, but you have AP allele, left side, which is only for the sake of particular environment. That expresses, you provide that particular environment, that is salt stress, and it expresses under salt stress, and you have salt tolerance happening. You remove salty environment, and that expression is gone, and AP allele is lost. But there are some, like AP allele 2 or 3. How AP allele 1, 2, 3 are differentiated? You have 3 different marks. There is only one mark in AP allele 1, methylation mark. You have 2 methylation marks. There are 3 methylation marks in the promoter region. The box is the coding region of the gene, and the upstream to that, left-hand side is that particular box which is given and highlighted, and that is the kind of methylation sites. And that might be leading to silencing of the genes, and loss of gene function might lead to gain of trait. The repressive mechanisms are silenced, and beautiful genes or traits are expressing. And often it has been found in nature that the loss of gene function, but gain of trait, and mutations have led to that. AP mutations have led to that. And I highlight one example. So this is what is getting fixed. And this stably inherited AP mutations can be harnessed for crop breeding. And that kind of environment can be actually, favorable. Even if there is a drought or salt stress or disease, doesn't really matter. In Arabidopsis, very interesting, they have crossed a mutant, which is mutation for methylation. Methylation doesn't happen. Methylation doesn't happen. DDM1, which is here, methylation doesn't happen, no methylation. But the wild type is heavily methylated. When you make, and there's no other change. There is no other difference between these. They have sequenced. There's no other change between these. Mutation is only with regard to that DDM1. If you make a cross and get the recombinant inbred lines, you can see different AP alleles, different regions differentially methylated, and giving you different traits in the RILs, recombinant inbred lines. Mind you, they are derived from 2 neuro-isogenic lines. And that is for methylation only. They differ only for methylation. Methylation means the methyl group, CH3 group is added there. And you can see early flowering in that population. This is published. Frontier in Plant Science, you can see 2022 paper. Summarized there in that review. High biomass, long root, club root resistance. And you can see how methylation can play and give you traits which are agronomically, economically so important. So this is one area we have not really studied so much. So nurture is not just sake of nurture for that particular generation. We have to go beyond. Yes, in fact, this is another important point which is also published recently in Frontier in Genetics, and how seed is exposed to stress, and how methylation happens there, and how that methylation change goes to the seed generation, next generation, and gets fixed. In other words, changes could be directional. Epigenetic changes could be directional, can be directed, could be inherited, could be adaptive. So, directional evolution, directed evolution, Lamarckian concept, directed evolution, a beautiful example. And you can see that how you can do this in other crops, including rice. The directed evolution. So not that anything happens in nature, just it happens, and because a particular situation gets selected, it happens for a cause. It happens under a particular situation. Genome reshapes itself. And that was happening in tissue culture situation. We used to get somaclonal variation. It happens in response to tissue culture as a stress. And today, it's seen under stress situation, genome restructures itself, evolves itself, changes itself, and you have a change. And that change also gets transmitted. So that's something interesting. And you will further explain under high heat situation, what all happens and how different genes are getting. And you can see this in Frontier in Plant Science. They're all very recent papers, 2021 to 2022 papers. And read those, and you will understand this area much better. And for 25 generations, they have tested 25 generations in Arabidopsis. So you should not worry that for 25 generations, they have gone, those changes have been transmitted. In rice, we do not know whether it is happening already. Whether that, what is the, what is the methylome of Swarna? Why it is so stable? Why it performs so well? It will be interesting to know. So this is what is highlighted. If you read the last one, Rosen is derived from multi-generational, 25 generation heat stress displayed a notable adaptation in the context of phenotypic, genotypic, and epigenotypic resilience. How interesting it is. How stress is directing evolution. How stress is directing evolution. In gene banks, we have arrested evolution. In gene banks, underline, in gene banks, we have arrested evolution. In our swamps, we are allowing our evolution. So that's the reason why I keep emphasizing evolution gardens. So maintain evolution gardens. Let the crops evolve naturally. Let the genotypes be maintained under field situation. Let them face the vagaries of the nature. Let them die. You have seeds anyway in the gene bank. Let some of them die. Let them face the climate change effects and impacts. Let them come out of that by restructuring the genome. They will give new signs. And you can discover new signs by way of that. And they will give you new technology, new varieties. And this is the beautiful example that how by exposing, re-exposing, and all that for 25 generations, you can see those changes happening. Next one. Next one. You can change. So this is not working, so I'll ask next one. So this is very important. And this paper you should read. This is Trends in Ecology and Evolution, 2021 paper. Read this. You can see, because of genetic plasticity, you have epimutation. There is an alteration happening. And you can see there are 3 changes happening in that fish. And because of that, there is an adaptive change that is called genetic plasticity. And then you have a different color appearing. Okay? And in subsequent generations, so what is written here? Genetic assimilation of plastic epigenetic change. What happens after prolonged environmental exposure? Getting fixed. That is something which is very, very important. I didn't know this. This is eye-opening for me. That genome first is acquiring a epimutation. and after some time converting that to a kind of mutation. Something which is new to me. And this is what is actually highlighted here. The lollipops represent epigenetic modifications, while yellow bars represent genetic variation. And after a certain period of time, the pure and facilitated epigenetic variants in F1 may result in genetic variants in FN in future generations. That is something which is, unthinkable. That is happening. But anyway, and this is hardcore science. And I don't want to really explain this, because only those who have background would be able to understand how to really create. You can also in the laboratory create these AP alleles. You can create AP alleles. And in a particular environment, to face a particular climate change situation or management situation, ideal management situation, you can create a AP allele. You say that this fertilizer nitrogen efficiency is 30%. I want 80%, and carry out AP mutations and see if those AP mutations can remain stable, at least for a generation, if you can make them, and then provide that kind of environment. So your nitrogen is utilized 70%, 60%. So you can create in the laboratory. There are different ways, through tissue culture, through chemically induced mutation. All these are easier, you can do. But you can also, using CRISPR-Cas, gene editing technology, you can also carry out such changes and introduce some changes in the methylation pattern at the desired site. If you understand which site is important in a gene, and then create an AP allele, and AP allele would be giving you a trait which is not existing. And same thing explained there. We thought this field is very, very important. So I asked one scientist and IRI to work on this. So these are some of our papers which we published recently. So we published a review. This is epigenetics of modified DNA bases, 5-methylcytosine and beyond. And then dynamics of DNA methylation and its functions. Highly cited this one now, globally. And Suresh and myself published this, Frontiers in Plant Science, in 2021. And this one said that there could be applications, and cited some examples, stray examples in various crops. We also saw the transcriptome, the transcript undergoing methylation, demethylation. And that is adding another dimension to the gene expression. It is not that transcription is there and translation would happen. May not happen. Protein may not be produced. Transcript may be unstable, doesn't get spliced. If splicing doesn't happen, a productive transcript mRNA is not produced at all. Unstable transcript is produced because of methylation. So methylation plays such an important role. And that's the paper which highlights. So someone who's handling wants to go fast. So I'll go fast. So this is, go fast, next one. So this is our paper recently published. If you have POP1 QTL, you know POP1, we give phosphorus tolerance. And how it influences the methylation components, epigenome, and through that, how it gives you low phosphorus tolerance. A QTL influencing the epigenome and leading to differential gene expression and low phosphorus tolerance nil, NIL23, or PUSA44, highly productive ones, variety. PUSA44 and the near isogenic line, they were compared and recently published, that's written there, recently published. And you can read this paper, how epigenome is very, very important, how a QTL operates through the epigenome. So acquired changes which are not genetic which are not genetic but epigenetic, can bring so huge changes and very significant changes, and very importantly, agriculturally important changes. And their nurture matters because your environment, as I said in the beginning, can create such changes. Next one. Next one. So how to nurture rice for better performance? How to nurture rice for better performance? Can we create appropriately selected adaptive mechanisms? Can we first of all identify them? Or provide good agriculture practices? Have we defined good agriculture practices? Every soil type provides different challenge. The dryland ecology and the irrigated ecology provide different challenge. The upland and then hilly ecology terrains provide different challenge. The acid and saline soils provide different challenge. Site-specific nutrient management we talked about. Where is the solution? Have we reached somewhere there? And today we talk of precision agriculture. Can precision agriculture happen for rice? How feasible it is? Can we have that environment which is ideal for a epigenome to productively contribute to enhance productivity and production sustainably, with less water, with less nutrient? Can it do? There are some developments in this area, but lot more to be done actually. Can the microbiome contribute to this? Yeah, another layer of complexity. The rice microbiome is very poorly understood. They're only tip of the iceberg. Globally, not only in India, globally. And we know even our behavior, our thinking process, disease expression in human is controlled by the microbiome. The microbiome. I was in IMTech, I was talking to the director of IMTech, and he's a man working on epigenetics. And he said to me, there is a connection. So what microbes are doing? We don't really understand much. We try to manipulate the crops without bothering about the microbial load which is there as endophytes. How important they are. Next one. So this is a beautiful example which was published in 2018 in Science Reports. Might have seen, some of you might have seen, and some of you are already using in breeding. This particular allele was SPL14 allele, which gives large number of branching in the panicle branching. And what it gives? More yield. And Dr. Jena and his colleagues at IRI, they worked, transferred to different backgrounds, 4 different backgrounds. And there was another epi allele in IPA1. I mean, IPA1 is another form, Dr. What is your name? I forgot. Parameswaran. That doesn't really give that effect as this particular one. You might have read this paper. So there are different epi mutations, not every one of them giving the same effect. So Dr. Mohapatra, you worked on this, that how heavy panicle happens, and you have your own research work published in very high impact journals. And this, they discovered that it's not because of gene sequence difference. It's because of epigenetic difference. This difference in 2 alleles, the epi allele is because of methylation difference, not because of genetic difference, gene sequence difference. And when they transferred this epi allele, and you can see the lower panel, the corresponding recurrent parent is given on the top, wild type and corresponding recurrent parent, 4 recurrent parent B, C, D, E on the top, and the derived one through backcross, the derived marker assisted backcrossing, and they derived these lines. and what extent the grain number increased and yield increased, extrapolated to tons per hectare. And you can see grain yield increased by 28 to 83%. Parameshwaran. So, and the best check, yield advantage 64%. Just one locus. AP allele. There's a difference in methylation. We haven't studied methylation pattern in rice to the extent that we can do selection. And they have done this. So this is the kind of example, this is a historic one, that in nature it has happened. There will be many such alleles. And there are other examples in tomato, in maize. There are other examples. Next one. And there are traits and how they differ. Next one. Next time, I don't know. Next one. So we thought probably precision agriculture would give us ideal situation for rice to express its all potential to the fullest possible extent without sacrificing the environment, so that sustainably we can increase rice production. We initiated this. We started discussing 5 years ago. We have been so slow. And there has to be a recommendation that there has to be fast pacing of this activity in the council for rice. There should be a recommendation this Congress should recommend. There should be a recommendation on strengthening studies on alleles, epigenomics, and epigenetics. First of all, to understand, discover, and then subsequently manipulate crops for a generation and for several generations. So this we initiated across crops and others. So I believe we should be able to upgrade this. DG Saab is not here. We should be able to, there should be a recommendation. We should be able to upgrade this to a AICRP so that there is an institutional framework to define precision agriculture for rice and for other crops as well, and commodities, fish and animal as well. Next one. And you can see what all is happening and what is being used: soil health, crop health, decision support, and the variable rate applications, and then post-harvest, precision dairy, precision fishery, and so on and so forth. Next one. And you can see how spectroscopy is being used for soil health monitoring. Near infrared, very near infrared, mid infrared, and everything. So all that is being used to understand this. Next one. Soil fertility mapping is happening. Why? You can say why. Because we are so grossly insufficient to do gap, provide gap in case of rice. At this point in time, we are so grossly insufficient to provide the right kind of gap for rice. If you don't understand rice soil, in a particular field of 1 hectare, there will be variation. So obviously crop yield in different patches would be so different. A big patch, big field in IRI farm, soil fertility mapping where it has happened. So all these have been utilized, the technology, imaging platforms using drones. And drones now, is being employed. Can we use drones for farmers? You can use for spraying urea or for that matter, pesticides. But beyond that, doing precision agriculture, can you use drones? What all you can do in real time? A long way to go. There has to be investment. Who is going to use drones? Farmers do not have resources to purchase drones? Where are the facilities? 1 lakh drones is grossly insufficient. Farmers are small and marginal. Where is the technology that can give you decision support real time? So I think a lot more to do to use drones, employ drones in agriculture and rice particularly, to have that kind of nurture for rice. Nurturing rice for sustainable productivity gains. That is the point which I started with. And that is what I am highlighting and emphasizing. And that is what should be the objective. How do we really create that for future? Next one. Next one. And this is the digital soil map of IRI. Next one. You keep doing all this to understand where to be applied and how much fertilizer to be applied without wasting the resources and cleaning the soils, drone-based. And all that you can do, RGB, multispectral, hyperspectral, and particularly hyperspectral is so important. When you were creating, phenomics facility at IRI, we only added hyperspectral imaging. Dr. Ravi Sahu suggested. Nowhere in the world the hyperspectral imaging was there in imaging platforms, in phenomics platforms. We were the first to really include that. That's one of its kind. Now people have started including. So now you can do all kinds of mapping and you can do satellite mapping. So a plethora of ways are available with us. Can we intelligently deploy them? अब सॉइल मैपिंग करते करते अगर 10 साल लगेगा रिमोट सेंसिंग से, जैसे हम लैंड यूज प्लानिंग करते आए हैं, कभी देश का नहीं हो पाया, अभी भी नहीं हो पाएगा एट हाई रिजोल्यूशन, और 10 साल के बाद और कुछ टेक्नोलॉजी चेंज हो जाएगा. So can we really create this in shortest possible time? How do we help precision agriculture in rice to happen? To provide that kind of productive environment without sacrificing, compromising the natural resource base. Next one. Next one. So, IoT-based decision support system for irrigation. Rice. Can there be a recommendation that the farm in DRR, I don't know, some people from DRR would be here. DRR and CRRI would be based on IoT. There should not be flood irrigation. Forget about the farmer's field. In all ICR research institutions where rice is being cultivated, it would be only IoT-based irrigation system. You are sitting at the lab, your mobile operates your pumps, and irrigation is done for rice. Extra water cannot be pumped and should not be pumped. If you feed more, what will happen? You will have disease. More nutrition, more water. Rice is aquatic, semi-aquatic, perfectly all right. Breed for situations where there will be more productivity with less of water. This is what is important. Build that kind of epigenomes. Select that kind of epigenome which utilize the available resources minimum or rather optimum to give you best performance. And this is what is very, very important. Phenomics is only a tool. Use of hyperspectral imaging is only a tool. CRISPR-Cas editing is only a tool. How do you translate those to field situations and develop something useful and help farmers in the long run? Next one. So, go back. So this is what I have already said. I don't want to really repeat anything. Next one. So let's go to next one. And this is another dimension of it. The holo genome. What is holo genome? The plant genome, animal genome, microbial genome, all this. But rice plant is not rice plant without the microbiome, the endophytic domain of it. millions and billions. They are sitting inside. What they are doing? The holobiome is microbiome plus plant genome, the chloroplast genome, the mitochondrial genome, the nuclear genome, all this, and gene transfer happening horizontally. And we say that these genomes have come from somewhere. The chloroplast has come from some other source to plants in evolution. So holobiontenase, that the two genomes staying together, cooperating with each other, and in certain instances giving resistance. I had a student called Dr. Prabhu Patel. He did MSc at IRI. So intake, I was going there. He came to receive me. I didn't know that he is the person. I had forgotten. So he said, "Sir, do you recognize me?" I said, "No, I mean, you become fat, you lose hair, there's complete transformation. So you don't really recognize after 20 years or 15 years. So I said, "Yes, I can recollect your name, but I was not able to connect." Yes, sir, you taught me that, this and that. And I have discovered a xanthomonas, which inhibits the pathogenic xanthomonas, the bacterial leaf blight pathogen in case of rice. Another xanthomonas, and he did PhD with Dr. Sonti, and he has given that xanthomonas sontai, and you can see that. And that inhibits the pathogenic xanthomonas to grow on rice. Beautiful example. I gave given this paper, I have not cited. Example that how the holobiome is so important. When we will study, should we study? There are new dimensions to what we are discussing today. And this is what is actually happening already. We are trying to introduce a drape gene. Arabidopsis drape gene, I transferred to rice plant, for instance. And that gave salt tolerance and then drought tolerance to rice. Why? Because there are drape responsive genes. That drought response binding element, so that is that binding protein, that drape is a protein, it's a transcription factor. It goes and binds. And a number of genes are actually transcribed. So and similarly, oxygen response element, where a particular protein binds, the receptor protein, and a downstream genes which are responsible, they respond to oxygen, they get expressed. All these happening, getting induced because of microbes. Already, they're widely published. But we have not been able to engineer, rather produce that kind of inoculum which will help us. Dr. Pal at Groundnut Institute identified one bacterial or fungal strain, whatever, microbe, which gives drought tolerance. He inoculated groundnut in Anantapur district of Andhra Pradesh. And he told me that it gives higher yield under drought situation. I don't have many examples. But if you understand this holobiome, how they cooperate, how they live together, and how they influence the genome and epigenome, the metabolome, the proteome, and ultimately the phenome. In breeding, we don't take into account. Somebody told me, and my wife told me one day, "Oh, you have bred some kira." Doesn't really give that feeling. Earlier, we used to have that kira. It used to be so good. Today, there is no taste at all. What is this kira that you have bred? And you say the yield is increased and all that disease resistance increased. The taste is not there. So basically, I have been emphasizing this, I told you here once, that we don't do that kind of studies. So there is a need to really incorporate this wherever required, this kind of studies. And you can see a whole lot of things, salt tolerance is explained and how it happens. What are the sensors and endophytes? They are producing siderophores, phytohormones, and metabolites, and they are going to binding to receptors or sensors inside cell, and that is leading to triggering of gene expression. Wide array of genes, very well studied now, and it is high time that in rice we do this and create inoculums. When I was here, Dr. Urmila Dua told me that the seed microbes, they give resistance to rice blast. I don't know where is that study. Dr. Arup Mukherjee says that his trichoderma, whether it is goes inside and where it stays and how much it is studied, I don't know. It gives seed blight resistance. There will be n number of such situations. And we need to really build this part of the story to nurture rice further for higher productivity. Next one. So what message we should take home? I have taken more than 1 hour. What message we should take home? I will not say summary, I will not say conclusion. I would say message. What message we should take home? One, should we have another international year on rice? When it becomes 25 years of first international year of rice in 2004, where we said rice is life, how far we have gone, what we have been able to do, 50% of population being fed, 2050, another 25, 27 years. Can we reach there? 70% increase in rice production for global population, meeting diverse needs. Sustainably increase rice production. Refocusing our attention on that. Another international year of rice. Can there be a recommendation? Let rice evolve in nature. These swamps are vanishing. Swamps are vanishing where rice used to evolve in Northeast India, in Eastern India. Where rice would evolve, not in your gene banks. Let rice evolve. Let us recommend that we must create an environment for evolution to happen in nature. The community gene banks, the field gene banks, provide support so that they evolve there in nature. And more of epigenome alterations, genetic alterations happens. More intensive studies on rice epigenome and epigenetics, epigenomics and epigenetics. I have said already. Epi alleles, those who have impact on crop phenotype, only then I call them alleles. Not because there is a change, it becomes allele for me. Any change that has an impact on phenotype. So discovery of those, not many are discovered. There are some discovered with regard to adaptation, some discovered with regard to domestication, some discovered with regard to agronomic traits, disease resistance, yield, but whole lot of things remain undiscovered. Designing precision rice agriculture, precision agriculture for rice, long way to go, so that best environment is provided to nurture rice to give that kind of phenotype. And defining good agriculture practice for every situation. Imagine the kind of diverse ecologies and niches in which rice is being grown. and giving that kind of recommendation. Fertilizer recommendation 80, 40, 40 will not work. That's not precision agriculture. So giving precision agriculture for rice, and finally going deeper into the rice microbiome and the world of endophytes to effectively nurture a holobiontic synergy for sustainable production of rice. How do we really do that and manipulate that and change that? Can we really change? Microbes can be also targeted for AP allele alterations and creations through CRISPR-Cas systems. And I believe plenty of opportunities are there. And those working on crop production, for them to define situations, environments for best performance of rice, a long way to go. I must say, a long way to go. Whatever we did is not really good enough. There's plenty of opportunity for us to work. Thank you very much. And we must thank the farmers. We are all here, very nicely enjoying the cozy environment. It's hot, you provide AC. It's cold, you provide heater. It's a hot food, cold food, as you wish. And you fly. But farmers are toiling in the field and providing everything. And let us think about them and work for them. Sacrifice. How much we can sacrifice. That will determine the fate of the farmers. So wish you all the very best. The Congress is already a successful one. And 2 more days of deliberations. I wish all the very best. Thank you very much for inviting me. Thank you. Thank you, sir. Thank you.
Thank you very much, sir, for such an enlightening, elaborate, comprehensive, and informative talk. You have nurtured our thoughts in such a way that following the Darwin's principle, our nature will also change. We will increase our efficiency, and certainly we will develop sustainable rice production system in future. Thank you very much, sir. Now, as a token of love and respect, I would like to request our Director NRI to please felicitate today's speaker with a shawl and memento. Thank you very much, sir.
Sir, after such a scintillating talk, I can simply say thank you. You come again and again and deliver such type of lecture in future to NRI scientists. Thank you.
Very good evening to one and all, to all the dignitaries and all the participants here. Now it's time for ARRW award ceremony. For this, I would like to invite President ARRW, Dr. P.K. Agarwal, Secretary ARRW, Dr. Sanjay Shah, and SSC Patnaik, sir, Member Secretary Award Selection Committee, to come on the dais. Sir, please. Now I will request Patnaik sir to please read the citation of the awardees. SSC Patnaik sir, please.
Good evening, all. Now we are in the session of ARRW Fellow Awards and the Best PhD and Best MSc Award. This award was formulated by our ex-director and present DG, Dr. Himanshu Pathak, sir. And for making the judgments, there was a committee headed by Dr. L.M. Gannayak. And the committee, based on several criteria, they have identified the awardees. And now I will request Dr. SSC Patnaik, sir, who was the member secretary of the award committee, to read the citations and call the awardees one by one. Thank you, sir.
Good evening, everybody. Respected Dr. P.K. Agarwal, President ARRW, and ADG ICAR, Dr. Sanjay Shah, Secretary ARRW, and other dignitaries and delegates. Actually, we were conducting it in the ARRW general body meeting, but this time we thought that it will be a better opportunity if such a array of delegates will be there, as we are finding that our ex-DG, DG ICR, Dr. Mathilochana Mahapatra is there. It is the best opportunity with whom we can get support opportunity to present the awards. Firstly, I am thankful to the organizers for giving me the opportunity to introduce and provide brief achievements of the rice workers for ARW Fellow Award. There are 5 fellowships, one each from crop improvement, crop production, crop protection, basic science, and social science disciplines. And they were selected for this year by 5-member judging committee, as it is already declared. Straightway, I'll go for the candidate 1. Candidate 1 is Dr. A. Anandan, and his achievement is Dr. A. Anandan, principal scientist and head regional station in charge of ICAR, Indian Institute of Seed Science, Bangalore. Completed his MSc AG from Tamil Nadu Agriculture University, Coimbatore, and PhD from Annamalai University, Tamil Nadu. He started his professional career as assistant professor at Annamalai University, later joined as senior scientist and ICAR, National Rice Research Institute, Qatar, and continued as principal scientist till 2022. He received NEWS India UK Research Fellowship 2017, Fellow of the Indian Society of Genetics and Plant Breeding 2021, Association for the Advancement of Biodiversity Science 2015, Sub-Eminent Agricultural Biotechnologist Award 2014. He has released 11 rice varieties for aerobic and irrigated conditions through CVRC or SURC, and published more than 95 research articles in peer-reviewed journals. He identified QTLs superior haplotypes for the shoot and root vigor, anaerobic germination, low nitrogen and phosphorus tolerance in rice. Sir, I propose the name of Dr. A. Anandan for admission to the fellowship of the Association of Rice Research Workers, Qatar. I request that he may be admitted, sir. Anandan, please come.
Let me take a photo. Please come. Dr. A. Anandan, on behalf of the esteemed members of the Association of Rice Research Workers, Cuttack, it is my honor to admit Dr. A. Anandan as Fellow of the Association, and I urge him to serve the Rice Science and Society.
Sir, our second candidate is Dr. Sukant Kumar Sarangi. May I call him that he can, while I am reading his citation. Dr. Sukant Kumar Sarangi, Principal Scientist, ICAR, Central Soil Salinity Research Institute, Regional Station, Canning Town, West Bengal, obtained MSc from OUT Bhubaneswar and PhD from BHU Varanasi. Dr. Sarangi started his career as scientist at ICAR Regional Center for NEH region, Meghalaya in 2003. He has made outstanding research contributions in developing package of practices for growing rice under hill agriculture ecosystem in a farming system approach, and developed technologies for better crop production in salt-affected soils of India, conservation agriculture and cropping system intensification in the salt-affected coastal zones. He has published more than 90 research articles, 13 review articles and book chapters, 30 popular articles, 16 technical bulletins, 3 books and manuals, and presented about 100 papers in seminar and symposia. He has established strong research collaboration with several countries such as Australia, Philippines, Vietnam, Bangladesh, Nepal, etc. for management of coastal salt-affected soils of India. He was conferred Fellow of Indian Society of Agronomy in 2019, Fellow of Indian Society of Coastal Agricultural Research 2020. Presently, he is serving as editor of Indian Journal of Agronomy and Journal of Indian Society of Coastal Agricultural Research. Sir, I propose him the name of Dr. S.K. Sarangi for admission to the fellowship of the Association of Rice Research Workers, Cuttack. I request that he may be admitted.
Dr. S.K. Sarangi, on behalf of the esteemed members of the Association of Rice Research Workers, Cuttack, it is my honor to admit Dr. Sukanta Kumar Sarangi as Fellow of the Association, and I urge him to serve the Rice Science and Society. Thank you.
Sir, our candidate 3 is Dr. Lambodar Behera. Dr. Behera is working as Principal Scientist, Crop Improvement Division, ICAR, National Rice Research Institute, Cuttack. He did his MSc Biotechnology from TNAU, Coimbatore, and PhD Genetics from Osmania University, Hyderabad. He started his career as a scientist biotechnology ICAR National Rice Research Institute, Cuttack in 1998, and has significantly contributed in the field of rice molecular breeding, molecular biology, and genomics. He has significantly contributed for the development of 19 rice varieties suitable for different ecosystems of India. He has worked on identification of genes and QTLs for resistance of BPH, gallmease, root knot nematode, and sheath blight disease. Yield and yield traits, tolerance to cold and drought. He has published 88 research articles in reputed national and international journals. He has edited 2 books, written 36 book chapters, 2 popular articles, 11 technical research bulletin, 2 practical manuals, and handled 12 research projects financed by external agencies. He has successfully guided 8 students for PhD and 36 MSc Biotechnology and Bioinformatics degrees. He has received Fellow of the ISGP 2018, that is the Indian Society for Genetics and Plant Breeding, New Delhi. Sir, I propose the name of Dr. Lambodar Behera for admission to the fellowship of the Association of Rice Research Workers, Cuttack. I request that he may be admitted, sir.
Thank you. Dr. Lambodar Behera, on behalf of the esteemed members of the Association of Rice Research Workers, Cuttack, it is my honor to admit Dr. Lambodar Behera as Fellow of the Association, and I urge him to serve the Rice Science and Society.
May I request Dr. P.C. Rath, please? Our next candidate is Dr. Prakash Chandra Rath, Principal Scientist, Crop Protection Division, ICAR, National Rice Research Institute, Cuttack. He has completed his MSc AG from OUT Bhubaneswar and PhD from BHU Varanasi. He is having 30 years of rice research experience in agricultural entomology. He has worked in host plant resistance, chemical pest management, and integrated pest management in rice in research farms as well as farmers' feed. He is associated with the development of 7 rice varieties, out of which Shihardan 317 is proved to be BPH resistant. He has developed different products like NRRI Trichocard, NRRI Bacon card, and NRRI biostimulants. He received the Fellow of Society for the Protection of Environment and Sustainable Development in 2000, Fellow of Applied Geologist Research Association 2007, Fellow of Plant Protection Association of India 2012, Fellow of Indian Climate Congress 2018. He received 42 different scholarship and awards and published 109 publications in reputed journals and 31 technical bulletins and 40 popular articles. Sir, I propose the name of Dr. Prakash Chandra Rath for admission to the fellowship of the Association of Rice Research Workers, Cuttack. I request that he may be admitted.
Dr. P.C. Rath, on behalf of the esteemed members of the Association of Rice Research Workers, Cuttack, it is my honor to admit Dr. Prakash Chandra Ratha as Fellow of the Association, and I urge him to serve the rice science and society.
Now I will request our fifth candidate to come into the dais, Dr. G.A.K. Kumar, please. Dr. G.A.K. Kumar, Principal Scientist, ICAR, National Rice Research Institute, Cuttack, completed his master's and doctorate in agriculture extension from ICAR, Indian Agriculture Research Institute, New Delhi, in 1990 and 93, respectively. He has 30 years of experience of working with national and international organizations and university. His area of specialization is social simulation, research methodology, entrepreneurship, startups and FPO formation and promotion. He has developed many models, including RAJSIM, a computer simulation model, and 4S4R, that is self-sufficient sustainable seed system for rice. Inspire 1, that is innovative extension model for fast spread of varieties in rice ecologies. And Inspire 2, that is innovative extension model for fast spread of ICAR technologies in rice ecologies. Dr. Kumar has more than 100 publications, including research papers, books, and book chapters, and popular articles. Sir, I propose the name of Dr. G.A.K. Kumar for admission to the fellowship of the Association of Rice Research Workers, Cuttack. I request that he may be admitted.
Dr. G.A.K. Kumar, on behalf of the esteemed members of the Association of Rice Research Workers, Cuttack, it is my honor to admit Dr. G.A.K. Kumar as Fellow of the Association, and I urge him to serve the rice science and society.
Thank you, sir. With this, we come to the end of the fellowship award, but along with that, we have 2 more awards of PhD and MSc thesis. The best PhD thesis award for the year 2022. The Association of Rice Research Workers also introduced the award for outstanding PhD thesis on rice science from the year 2021. And Dr. Richa Sao of Indian Indira Gandhi Krishi Vishwavidyalaya, Raipur, was selected for the award Is she there? Please. She is selected for the award 2022, and her thesis is entitled on the effect of gamma rays on traditional rice at phenotypic, genotypic, and transcriptomic level. Her research relies on induced mutation breeding for environment of 3 popular traditional rice varieties of Chhattisgarh state. And the major outcome of the work was release of an aromatic short-grain mutant variety, Trombe Chhattisgarh Vishnubhog mutant by SIRC. Our next is the Best MSc Thesis Award for the year 2000. Association also started in 2021. And for 22, it goes to Ms. Alma Fatima M. from Tamil Nadu Agriculture University. Is she there? Okay, okay, please come to this. Ms. Fatima from Tamil Nadu Agriculture University, Coimbatore. She is selected for this award 2022 for her thesis entitled Bulk Segregant Analysis of Therapeutic Traits in Rice, Oryza sativa L, and in F2 population of ADT R48 into Kabuni. Now we come to the another one best case bearer paper award, of which the authors are Veena Vigneswaran, Deepa John, Shipak S, Deepa Thomas, and Surika Srilatha A.K. Srilatha. Anybody from them is there? Best paper बस कल ना okay. With this we come to the end of the no case bearer award best paper मैं पढ़ दिया ना Veena Vigneswaran, Deepa John, Shilpa. Anybody I called, na? Anybody? Deepa Thomas. Okay. From that institute, if anybody is there. Thank you very much for coming and thank you and thank you, sir. With this, I congratulate all the awards, all the success and prosperity in their career. And with this, thank you.
From my side, thank you, everybody. Thank you very much. Particularly the committee who did a good job for this society. So thanks everybody. And thank you also, all of you. And I'm thankful to you, sir, for coming and gracing the occasion to give the award. Thank you very much.
Sir, on behalf of ARRW, I thank Trilochan Mahapatra sir, Dr. A.K. Nayak sir, President ARRW, Dr. P.K. Agrawal sir, Sasank Patnaik sir, and all the members who are present in this auditorium for this award function. Thank you all. And now the cultural program will start.
A very good evening to one and all. Without wasting much time, we are moving into the cultural evening. We request you all, after the day-long deliberations, scientific deliberations, invigorating learning sessions, it's time to relax and rejuvenate with friends and family. For the purpose, the cultural evening has been organized. You are requested to stay back and enjoy the cultural evening.